destes no Japão, em Taiwan, na Turquia, na Roménia e no México. Hoje em dia já há mais. Aqui a ver dos que estavam em fase de testes. Neste momento os Estados Unidos está a avançar para um sistema de aviso antecipado operacional também. Aqui em Portugal também já houve testes, mas não está operacionalizado. E pronto, este aviso antecipado, é preciso dizer que ele não substitui de forma nenhuma a prevenção de longo termo, que assenta na construção do edificado que resiste aos sismos. Isso é uma coisa importantíssima e não pode ser substituída, mas é um complemento, porque permite às pessoas tomarem ações, terem ações de defesa, de proteção pessoal, porem-se debaixo da mesa, etc. E é particularmente importante, por exemplo, para a indústria, no caso de refinarias e por aí fora, portanto, no caso de indústrias críticas e perigosas, poderem fechar automaticamente coisas que têm de fechar para não haver explosões e por aí fora. Para comboios também, mesmo nos hospitais permite parar as cirurgias antes de chegarem movimentos fortes. Portanto, é um sistema com bastante valor, embora não sejam de todo um substituto da prevenção a longo termo.
Muito obrigado. E em relação a Portugal, nós temos, tanto quanto sei, previstos alguns sensores deste tipo a cabos submarinos. Creio que é essa a informação mais recente, certo? Poderia-me falar um pouco mais sobre isso?
Exato. Portanto, se calhar até era melhor ser o Luís Matias, não sei se o Luís Matias ainda está por aqui para falar sobre isso, porque o Luís é que está mesmo diretamente envolvido nesse projeto dos cabos submarinos. Estás por aí, Luís? Parece que não. Então, a ideia dos cabos submarinos é que nós temos fibras ópticas, né, enterradas no fundo oceânico ou colocadas no fundo oceânico, e estas fibras ópticas, elas propagam luz. E quando há uma vibração, essa propagação de luz é afetada. E deixa-me ver se encontro aqui fiber. Ok, eu tenho aqui um artigo, mas não é este. Deixa-me procurar submarine. Só para mostrar o bonequinho. Não estou a encontrar facilmente o boneco. Está aqui, está aqui. Ok, vou partilhar aqui este. Também não é? Sim, exato. New share. Aqui. Não está. New share. Este. Já está. Ok. Portanto, a ideia é que quando nós temos um sismo, esse sismo vai perturbar a fibra e, portanto, nós vamos ver uma perturbação naquilo que é o sinal transmitido ao longo da fibra óptica. Temos aqui uma comparação entre um registro feito na sequência de um sismo, um registro numa estação sísmica, que é este que aqui está, IV.HPAC. Esta é outra estação, MN.WDD, e temos aqui então a vermelho o registro feito na fibra óptica. E claramente vê-se aqui uma primeira chegada, não se vê tão bem, que é a onda P, e depois temos aqui um segundo pacote que será a onda S. Portanto, esta tecnologia é uma tecnologia que ainda está numa fase bastante experimental, e realmente em Portugal nós estamos a tentar instrumentar alguns dos cabos submarinos que temos, porque temos vários, como está aqui, como mostra aqui, temos vários cabos submarinos que saem de Portugal, que vão para a Madeira e para outros sítios, e nós estamos a tentar instrumentar alguns destes cabos para podermos utilizá-los como sensores sísmicos. Estes sensores são bastante diferentes dos sensores a que nós estamos habituados, porque os sismómetros eles basicamente registram diretamente o movimento do Sol, através do movimento de uma massa, que é uma massa inerte, e portanto a ideia é que a massa fica parada enquanto o chão mexe, e nós registramos a diferença entre o movimento do Sol e a massa que está parada. Aqui no caso das fibras ópticas, é muito diferente porque o sinal do sismo ele vai ser sentido ao longo de toda a fibra óptica. Portanto, é aquilo a que nós chamamos um sensor distribuído. Em vez do sensor ser sensível ao movimento num ponto, ele vai ser sensível ao movimento ao longo de uma linha. E, portanto, há ainda muito que trabalhar para conseguirmos perceber bem estes sinais. A grande vantagem é que realmente temos uma oportunidade de observar os oceanos que nos faz falta, porque é muito complicado pôr sensores sísmicos nos oceanos.
Muito obrigado.
Então espero que tenha respondido, que não tenha sido demasiado cansativo.
Não, de forma alguma. De forma alguma.
Ótimo, ótimo.
Pelo contrário.
Às vezes nós entusiasmamos, ficamos a falar.
Não, muito obrigado, agradeço bastante. Eu não queria monopolizar aqui o tempo, mas não resisto em colocar mais uma pergunta.
Também não está mais ninguém, as outras pessoas que estão são os colegas que vão estar cá o resto do dia. Estávamos a ligar e estávamos a ver os problemas técnicos que haviam no YouTube.
Esta pergunta é muito simples, tem a ver com a escala de Richter. Eu sei que não é uma escala linear, que é logarítmica. Muitas vezes existe a percepção do grande público que um sismo de 4 será o dobro de um sismo de 2, grau 2. No entanto, isso não acontece. No entanto, eu já fiz algumas, enfim, confesso que não pesquisei muito, mas encontrei valores dispares para o valor de energia que é libertado quando variamos um valor na escala de Richter. Afinal de contas, qual é que será o valor aproximado?
É aproximadamente 30 vezes.
30 vezes?
Acho que é 32. É um exercício que nós resolvemos todos os anos na cadeira de Geofísica Interna. Portanto, realmente é uma escala logarítmica. Uma forma que eu acho que é muito visual de mostrar isso é aqui este mapa, que mostra a subducção da placa do Oceano Índico por debaixo da placa de Sunda. Portanto, temos aqui esta placa indo-australiana a subductar nessa direção por debaixo desta outra placa. E esta região que está aqui pintada a verde é a área da falha ao longo da qual houve deslizamento, portanto, ao longo da qual houve ruptura. Durante o sismo de 2004 na Sumatra foi sismo 9.2. E para comparação, eu gosto de pôr aqui ao lado Portugal, a área de Portugal à escala, e nós vemos que basicamente são precisas 2,5 vezes a área de Portugal para termos a área da falha que rompeu durante o sismo de 2004. Agora, também para comparação, vamos olhar para outras magnitudes. Portanto, isto é um sismo de magnitude 9.2, é aquilo que nós chamamos de um mega sismo, é realmente um evento que liberta imensa energia. Depois aqui temos a azul, um sismo de magnitude 8.4, e a área da falha ao longo da qual houve deslizamento já é uma coisa muito mais pequena. Aqui um sismo de magnitude 7.9, que é quase 8, são duas áreas muito, muito pequeninas. Um sismo de magnitude 7.3, aqui uma coisa muito pequenina. Portanto, realmente, aqui neste caso, a diferença entre um sismo de magnitude 7 e um sismo de magnitude 9 não é mais 2, é vezes 60 em termos de energia. 60 não, 32. Vezes 32.
32, não é assim?
Exato.
Isto deixa-me a pensar qual é que seria a verdadeira área de ruptura do sismo de 1755.
Pois isso é uma excelente pergunta sobre a qual não há consenso nenhum, porque nós não encontramos nenhuma única falha com uma área suficientemente grande para gerar um sismo da magnitude que observamos em 1755. Portanto, tem-se procurado muito ao largo de Portugal as falhas que estão ativas, elas neste momento estão bem mapeadas, embora elas sejam mapeadas com base em métodos de superfície e, portanto, nós conhecemos as falhas que afloram à superfície, mas não sabemos como é que elas são a profundidades maiores. Portanto, pode haver um desajuste entre aquilo que nós vemos à superfície e aquilo que são as falhas ativas em profundidade. Mas naquelas que estão mapeadas, nós não conseguimos encontrar nenhuma falha que consiga gerar um sismo da magnitude do sismo de 1755. Então, o que é que os investigadores têm tentado fazer? Considerar cenários de rupturas múltiplas, portanto, em que o sismo de 1755 é o resultado não só da ruptura numa falha, mas na ruptura em mais do que uma falha, e isso tem algum sucesso em explicar uma série de observações, embora também haja várias propostas das várias falhas que romperam em conjunto. E para além disso, também, mais recentemente, houve uma proposta de baixar a magnitude do sismo de 1755. Aliás, não é em vez disso, é a juntar a isso. Portanto, não só teria sido uma ruptura múltipla, como também a magnitude teria sido mais baixa do que aquela que está hoje em dia nos catálogos. Mas é um sismo muito, muito difícil de estudar, porque é um sismo um bocadinho fora de sítio. do ponto de vista que é difícil compreender um sismo daquela magnitude com aquilo que nós conhecemos da nossa região. E para além disso não havia dados nenhum na altura, né? Porque na altura nem sequer ainda se sabia que os tremores de terra eram gerados por rupturas em falha, não havia sismómetro, não havia nada. E portanto não há dados, os dados que há são só registros históricos, documentais, daquilo que as pessoas relataram, e embora sejam, em particular o inquérito do Marquês de Pombal é um inquérito muito completo, mas é sempre um tipo de dados que tem limitações muito grandes. Portanto, em particular para estudar um sismo que tudo parece indicar é que foi um sismo complexo, a informação que temos é pouca e, portanto, é um sismo com muita liberdade para nós imaginarmos cenários diferentes.
Muito obrigado.
Deixam uma margem de manobra muito grande. Ok, então, uma continuação de uma boa noite europeia do investigador.
Muito obrigado pela disponibilidade e por todas estas respostas.
Ora é essa.
Ora, por enquanto não apareceu mais ninguém. Susana?
Paula.
Isto está um bocadinho lento.
Agora então, não é Paula, agora é Inês. Não é?
Não, é Paula. É Paula.
Agora é a Paula?
Acho eu que sim.
Não, agora sou eu, Paula.
Não é isso.
Que eu tenho?
Não é isso. Eu queria te pedir o artigo das fibras ópticas, dos sensores de fibra. É um artigo,
okay,
não é?
Ok.
Ou pões lá na pasta, ou envias-me, ou pões na pasta do Google, não sei o quê, Drive.
Então ponho na pasta do Google, se calhar.
Está bem, então, obrigada. Agora é a Inês, sim. Eu não sei se o Luís está aí. Consegue-se pôr aquele fundo como a Susana tem?
Eu posso te enviar.
Não, mas eu experimentei na minha casa e como eu tenho aqui a parede de não sei de cor, aquilo fica tudo aos bocados, portanto não sei se vai funcionar. Mas podes enviar. Eu posso experimentar.
Deixa-me ver aqui.
Acho que tem que se pôr um pano verde.
Um pano verde? Não é preciso pôr um pano verde.
O que é que tu tens? Tens uma parede branca, é?
Não, eu tenho tralha atrás de mim.
Ai, consegues? Então envia lá. Envia a ver se eu consigo, pois.
Ok, deixa-me pôr aqui na Drive. Ok, então primeiro o artigo. Ok. E a seguir. Onde é que eu tenho? Não, pus aqui noutro sítio. Tanto organizamos que fica tudo desorganizado.
É complicado, muitas coisas abertas, não é?
Pois. Ok, já pus, estou por lá no Drive, já está. Faz o download da imagem. Ok. E no Zoom vais às preferências, carregas em cima onde diz Zoom US na barrinha.
Sim, mas eu não consegui ver nada na Drive.
Quer dizer, não consegui aparecer. Sim.
Pois, vou fazer aqui um refresh a ver se ele gosta. Então, o artigo é de marra. É, não é? É.
Exato. E o logo é Inês 2020.
Sim, já vi. E, portanto, tu dizes no Zoom, onde é que está o Zoom?
Ok. Vais em cima à esquerda, onde diz, a mim diz Zoom US, vais às preferências.
Em cima à esquerda não tem nada, mas está bem.
Não?
Não.
Mas a janela, não tens uma barra de ferramentas, aquela habitual que tem o View, Edit, janelas.
Sim.
Aí, em algum sítio, deves poder ter um menu que te dá as preferências.
Depois, acho que sim.
Eu acho que isto é diferente em Mac e em Windows.
Eu já fiz isso uma vez, mas depois não ficou, foi bem o fundo, mas agora não me lembro onde.
Deixa eu ver aqui.
Não.
Então,
Também não. À esquerda só tenho live em YouTube e mais não sei o quê. Deixa eu ver.
Ok. Não tens uma janela que seja Settings? Não chegou o e-mail com...
Em segurança, só se for segurança. Não, bloquear.
Não. Então espera lá.
É estranho, por uma vez já consegui fazer isso, agora não consigo. Porquê? A ver se pondo o vídeo, mas não é isso. Espera, pode ser. Pronto, é aqui no vídeo, seleciona um plano de fundo virtual.
Exato.
Eu vou ver se consigo então. Pronto, só que tenho que fazer o download, ainda não fiz o download do coisa. Tá, obrigada, vou experimentar a ver como é que fica. Obrigada. Tenho que fazer primeiro o download da... Agora, eu não vejo no YouTube, não vejo nada de perguntas, não consigo ver, não vejo nada.
Não, no YouTube não está a funcionar.
Pronto, é porque eu tinha perguntado se esta intervenção tinha sido através do YouTube. Ok, então foi através do Zoom.
Não.
Está bem, ok.
Foi aqui no Zoom.
Ok, ótimo.
Já há um YouTube que funciona. Eu posso pôr aí no chat.
Ok, pronto, olha, eu vou sair.
Ok,
bom fim de semana.
Obrigada, igualmente.
Deus, tchau.
Está a funcionar, há um novo YouTube que está a funcionar. Eu já mandei o link por e-mail e agora também está no chat. Há um novo YouTube que já está a funcionar. Portanto, vejam lá, ponham-se bonitas. Pá. Estão a ser filmadas no YouTube. Vai embora.
Eu vou experimentar partilhar a tela para ver se funciona.
Onde é que tem aquela opção de...
São os tais 10 segundos de diferença. Há 10 segundos de diferença entre o YouTube e o Zoom.
Então, mas não é aqui. Entretanto, posso fechar todas as outras janelas de YouTube? Em princípio, sim, não é? Tenho aqui várias janelas abertas.
Ok. Vão a ver o meu ecrã?
Espera um bocadinho, deixa ver. Espera.
Sim, estou a ver, Inês.
Já, já. Ok, obrigada.
Convém estar de olho na janela do YouTube, podem aparecer perguntas nessa janela, está bem?
Sim, vamos ver. Onde é que está? Por que não consigo ver? Espera que tenho que tirar o meu som, espera. Onde é que eu estou? Inês, peço desculpa, o que é que tu tens na tua tela?
Espera lá.
Não percebi.
Eu não sei como é que se compartilha telas. Mas pronto.
Pronto. Isto é a janela de YouTube. Já estás no YouTube.
Não está a ver. Estás a compartilhar alguma coisa?
Vê lá o que é que tu estás a ver.
No Zoom? Sim. Não sei, ver que tem vocês caras.
Lá agora.
Si está usando una silla de ruedas o un andador, frene o las ruedas si es posible. Luego cubra su cabeza y cuello y sujételos hasta que se detenga el temblor. Si se encuentra en una torre alta, agáchese, cúbrase, sujétese. Cuando se detenga el movimiento, use las escaleras, no use el ascensor. En una tienda o donde haya estantes independientes, muévase rápidamente a un área protegida, al lado de un carrito de compras o debajo de los percheros para ropa. Luego, agáchese, cúbrase y sujétese. Si está al aire libre, aléjese rápidamente de los edificios para evitar la caída de escombros, o lejos de las líneas eléctricas y otros peligros. Agáchese, cúbrese y sujétese. Si conduce, deténgase evitando los pasos altos, puentes, líneas eléctricas y otros peligros. Deténgase, ponga el freno de estacionamiento. Permanezca en el vehículo hasta que se detenga el temblor. Si está cerca de la costa, es posible que venga un tsunami. Agáchese, cúbrase, sujétese. Luego, párese y camine rápidamente a tierra alta o tierra adentro. Permanezca allí hasta que se levanten las restricciones del tsunami. Lo que haga durante un terremoto depende de dónde se encuentre, pero lo básico seguirá siendo lo mismo. Puede ser difícil correr o incluso caminar cuando el suelo se está sacudiendo. Déjese caer y arrastrarse si necesita moverse a un lugar más seguro. El mayor peligro durante un terremoto es la caída o el vuelo de objetos, por lo que debe protegerse. Proteja su cabeza y cuello con sus brazos u otros objetos. Los temblores como consecuencia de los terremotos pueden durar desde unos segundos hasta varios minutos. Manténgase en un solo lugar todo el tiempo. Para obtener más información sobre las acciones de protección contra terremotos y cómo prepararse, visite www.checkout.org.
Por esta experiência, eu ouvi a voz do Zoom e a voz do YouTube ao mesmo tempo com 10 segundos de diferença, ou seja, não percebi nada. Portanto, quem está a falar, se calhar não pode ter o YouTube com som, ou não sei bem como é que é.
Estamos hablando recién mientras me estaba maquillando, porque no sé cómo hacen fiesta aquí en España, pero yo quería dividir 25 dividido 5 y ellos me
Paula, mas tu podes desativar o som no YouTube.
¿Cuánto les dan? Y uno de ellos me dijo 5, pero asustado, porque uno
O
habla con
YouTube podes desligar o som.
yo divido 5 y digo,
Se não quiseres som.
Pois é. É o melhor.
Oh Paula, mas só ouves a voz do YouTube se quiseres. Exato, sim.
Pois, mas a Inês não tem os dois? É que pareceu-me que era a Inês que tinha os dois.
Sim, eu estava com o YouTube ligado.
Okay. Está bem.
Mas eu não sei se consigo, de facto é uma complicação. Esta história de ter o YouTube ligado ao mesmo tempo que o Zoom é um bocado complicado. Deixa-me lá tirar. Não, mas isto não tem som.
Então, já tens notícias? E então? Bom, está bem. Desde que seja na sexta. Bem, sexta, sim, sexta-feira pode ser, sim. Sexta-feira.
Luís, tens o microfone ligado, não sei se percebeste.
Terminology. When we talk about length of time, we tend to talk about this certain place. So this certain place are that relative
outer part of the Earth, overlying the asthenosphere, which is warmer and therefore more plastic material, not typical of generated earthquakes. But what goes on with this crust mantle core business? Those are chemical layers. The terminology is crust mantle core. Those are different chemical layers of the Earth. So the lithosphere, it turns out that cold, brittle plate moves in unison, has two parts to it. Upper part of the lithosphere is the crust. So if we have an oceanic lithosphere plate, let's say it's about 150 kilometers thick, its very upper part, about 60 kilometers.
We once thought that mantle convection below the tectonic plates could drive plate motion. Early textbooks showed mantle convection cells like in a beaker of hot liquid on a Bunsen burner.
Pois, há bocado não havia nada, não é?
Ginger, thank you. Coming up, more problems for a trouble.
Earthquake.
Yep,
We're having an earthquake.
Have you ever felt an earthquake or witnessed the effects of one? Seismic intensity, which is the shaking you experience, can be gentle or severe, short or long, jerky or rolling. Unlike earthquake magnitude, which is a measure of the energy released and is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is controlled by three main factors: the magnitude, how big the earthquake was; distance from the hypocenter, the intensity varies from place to place; and the local rock and soil conditions. Before we address each factor, let's clarify the difference between magnitude and intensity by comparing a light bulb to an earthquake. The light bulb represents the location within the earth called the hypocenter, where the earthquake begins. The magnitude, or size of an earthquake, is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb that is received at any spot in a room. A small light bulb in one area of a room will make that area bright with high intensity light, but it will leave the distant areas of the room dim with low intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking at different locations, as on a shake map.
Este é engraçado. Qual é que é?
Where do shake maps come from?
Inês, qual é que é este?
Sei. É um daqueles do primeiro link
After the
da
1906
Susana.
Ah, é
magnitude
do primeiro link?
San Francisco earthquake,
Eu acho que é da Iris.
using
Da
the
Sim.
Iris.
Alabama,
É daqueles.
Qual é o título?
Não é o sismo de 1906, é.
É?
Não. Acho que
É que
tem
a
a ver,
história da lâmpada é engraçada, pá.
tem a ver com intensidade e magnitude.
Exatamente, exatamente por causa disso.
Não, mas o vídeo diz qualquer coisa disso e depois é do sismo de São Fernando, sim.
Ah, está bem.
Eu ontem estive a vê-lo, por isso é que eu sei.
É o primeiro link, é o primeiro link.
The lower numbers generally dealt with how the earthquake was felt by people. The higher numbers were based on observed
Espera
structural.
lá, que agora estou aqui, espera só um bocadinho.
Human observations still help scientists understand earthquake ground shaking. But intensity is now measured by seismometers and illustrated by USGS shake maps, like this modern reconstruction for the 1906 earthquake. Colors represent peak ground acceleration. That is how quickly the ground shook and how swiftly it changed direction. The red zones reached 1G acceleration, or 100% of gravity, a violence of shaking illustrated in this shake table experiment. In the green zone, moderate shaking occurred with accelerations of up to 10% of gravity. Let's examine how intensity of ground shaking is controlled by earthquake magnitude. We understand that a 100-watt light bulb produces more light everywhere than a 25-watt light bulb. Similarly, Increasing earthquake magnitude also means greater intensity of shaking everywhere. To see this principle at work, let's examine two earthquakes that occurred at the same depth beneath Kumamoto, Japan, but had different magnitudes. On April 14, 2016, a magnitude 6.2 earthquake generated strong shaking up to 40 kilometers from the epicenter. The next day, a magnitude 7.0 earthquake released 20 times as much energy in the same location. Strong ground shaking extended to 100 kilometers from the epicenter.
Eu acho que agora acho que falta 5 minutos para eu entrar.
Stronger ground shaking, just like a larger wad of light casts brighter light everywhere in the room. Now let's examine how intensity of ground shaking is controlled by distance from the earthquake. This shape map for a magnitude 7.0 earthquake in Mozambique nicely illustrates a bullseye map pattern with intensity decreasing with distance along the surface away from the epicenter. Just like the light from a lamp is less bright the farther away we are from the lamp. By analogy, we expect shaking to decrease as distance increases away from the earthquake. Remember, earthquakes occur inside the Earth, not on Earth's surface. So let's consider the effect of earthquake depth on ground shaking intensity. To see this principle applied to earthquakes, let's examine two earthquakes of the same magnitude with nearby epicenters, but with hypocenters at different depths. In 2015, the magnitude 7.5 Hindu Kush earthquake occurred 212 kilometers below Afghanistan. Although strong shaking was distributed over a broad area, only 399 lives were lost. The hypocenter of the 2005 magnitude 7.5 Kashmir earthquake was only 23 kilometers deep. Severe ground shaking was concentrated near the epicenter, causing extensive damage to buildings, with over 87,000 fatalities. In 1989, the magnitude 6.9 Loma Prieta earthquake occurred on the San Andreas fault system near Santa Cruz, California. Ground shaking intensity and resulting damage was strongly influenced by local rock and soil conditions. In fact, the most severe damage occurred in Oakland and San Francisco's Marina District, 100 kilometers from the epicenter, where violent intensity 9 shaking was greater than that experienced by many areas closer to the epicenter. Both are built on mud substrate. A dramatic and tragic example of shaking amplification is the double-decker Nimitz Freeway constructed on bay mud. 4 seconds after drivers
Vou entrar daqui a 4 minutos.
shook and swayed, and sections collapsed, taking 42 lives. Seismograms from nearby stations document that seismic waves are amplified by a factor of 2 as they pass from bedrock to sand and gravel deposits, and the amplitude of ground shaking of soft and water-saturated bay mud is 5 times larger than on bedrock. The section of the Nimitz Freeway that collapsed Marina District was constructed on loosely compacted bay mud. In addition, debris from the 1906 earthquake had been dumped into the bay to make more land for city expansion.
Então o carro está bem, não. Quando pusemos os dois, tu disseste que ficava ali bem. Agora, passado um bocadinho, já disse que não está bem. Não, mas eu não posso ir lá agora. Agora estão 3 minutos para entrar, então não dá tempo de ir lá abaixo e voltar.
Following the earthquake and during
Mas
aftershocks,
não dá tempo para ir lá abaixo e voltar, tenho que falar.
mostly near the epicenter in the steep
Para
terrain of
falar.
the James Mountains
Não tenho
and
tempo.
along the rocky bluffs of the Pacific Ocean. In closing, if you feel the bump of an earthquake, it's important to know that the first waves may not be the strongest. Take immediate actions to drop, cover, and hold on before strong shaking arrives. That can save lives and reduce the risk of injury.
Tem aqui umas coisas muito pequenitas. Eu achei que o alerta também está aqui.
Paula.
Sim, Sim? Estás-me a ouvir, desculpa.
Olha, não se preocupe com o YouTube, que eu vejo o YouTube, está bem?
Está bem.
Pronto, eu fico aqui a ver.
Eu pensava que tinha o som desligado.
E pronto. Ok. A Paula agora?
Se tiver de ser.
Ok. Então vá.
Então,
Eu vou ficando por aqui também, está bem?
tá, tchau.
Vou desligar aqui o...
Ok, bom. Qualquer coisa.
Paula, também não ouço nada. Paula, está-me a ouvir?
Sim.
Ah, está a passar os vídeos sem som, então.
Desculpa?
Está a passar os vídeos sem som?
Não se está a ouvir?
Não, também não. É chato isto.
Eu ouço até muito alto, por isso é que eu não te ouvia.
Eu não ouço nada.
Deixa continuar então, aqui já agora para acabar este. 3 minutos. Não se ouve?
Agora estou a começar a ouvir.
Foi mais alto.
Não, mas assim eu ouço muito bem.
Alguém ouviu o som dos vídeos ou ninguém ouviu? Todos os vídeos tinham som.
Eu não ouvi nada.
Não sei se está mais alguém online ou se estão distraídos. Luís, Liliana, Miguel.
Miguel está no outro sítio.
Está só a
Não,
fotografia.
não ouvi
Não
agora não ouvi
som.
nenhum som. Há bocadinho ouvi aquele do sismo de São Francisco, mas agora...
Desligaste o teu microfone sem querer? Luís, estás interrompido. Interrompeste?
É propósito.
Está bem, desculpa. Ouviste aquele que passou a Inês, foi isso?
Sim, eu vi o Inês
o meu
agora...
não ouviste. O meu não ouviste.
Nada.
Lá. Então, aqui no meu microfone tenho o sistema altifalantes, o mesmo que o sistema, deve ser. Telefone, sair do áudio, não. O mesmo sistema, a ver. Vou experimentar outro vídeo, a ver se ouvem. Vou experimentar outro. Se vocês estiverem a ver, a ouvir, está aqui como se estivesse a funcionar o som. Eu ouço. Começou agora. Não estão a ouvir?
Não, Paula, não continuo sem ouvir nada.
Eu não sei como é que se faz isso.
Também não.
Não.
Não, nada.
Agora também não.
Também não.
Agora vou lanchar.
Continuam sem ouvir.
Nada.
Ah, é que isto está tão alto que eu não, quase que não vos ouço. Pus já no máximo que eu conseguia.
Agora estou a começar a ouvir qualquer coisa, mas nem se percebe.
Não ouviste o apito do Shake Alert?
Não.
Posso tentar ir traduzindo em simultâneo, tradução em simultâneo. Não sei. Já vi aqui as configurações do microfone. Só tem duas hipóteses, microfone é o mesmo que o sistema. Está todo o som no máximo para ver se o próprio microfone ouve o que está no vídeo. A coisa que eu tenho aqui é alternar para telefone, mas não posso ter aqui um telefone. Mas a minha voz ouvem.
Sim, muito bem.
Se estiver perto da costa e sentir tremer a terra, vá para um sítio alto e fique lá. Quando for para um sítio, isto é interessante, quando for para viajar, informe-se sobre os perigos desse sítio. Estás a ver? Por ali com as malinhas. Fale com a proteção civil e enfim, como é que se diz, as instituições desse sítio. Pois estes vídeos são engraçados. Olha, está altíssimo, tenho que tirar isto, que está altíssimo. Onde é que está? Cheguei.
Pois agora ouvi, esse bocadinho ouvi.
O quê? Música?
Sim.
Esta música?
Sim.
Então não ouves a narração e ouves a música?
Nada. Mas também ouve só os bochechos. Pronto.
Agora fui eu que parei. Pois, é pena, porque eles explicam isto tudo tão bem. Depois só se eu fizer a tradução simultânea, como estava a dizer. Ora, este já acabou. Agora andar para trás. E a ver se há aqui algo engraçado. Há aqui um que eu costumo mostrar nas aulas. Já não sei onde é que ele está. Eles são tantos. Aqui eu já pus o som mais alto que conseguia. Vamos lá ver. Aqui no compartilhar de tela devia haver aqui. Aham. Agora acho que vão ouvir que eu descobri aqui uma opção maravilhosa.
CAT scans produce 3D
Estás
images
a
of
ouvir ou
the
não?
inside of the human body.
Agora ouve-se bem.
The
Tinha
instrument
que pôr
uses
ali
an
uma coisa
energy
que dizia
source that
compartilhar
emits a
som
fan-shaped
no
beam of
compartilhar tela.
X-rays and a
Tinha que
receiver
pôr
or
compartilhar
X-ray
som do
detector on
computador.
the
E eu
exit
não vi
side
que
of the
estava lá
patient
esse
that
tiquezinho.
records a snapshot X-ray.
Estava sem tique.
Multiple snapshots
Tipo,
collected during one complete rotation are sent to a
Agora este está
computer
baixinho.
to create a
Este aqui nem é muito
cross-sectional
alto.
image or slice of the body.
Mas tu ouves.
Between rotations, the body is moved through the machine in increments with an image slice being computed at each position. Every rotation, here speeded up, yields an image of a new slice as it moves through the length of the target, in this case through the head of the person who is lying in the chamber. How simple seismology would be if we could do a CAT scan of our planet, but X-rays cannot penetrate the Earth. So how do we know what's inside? By using seismometers as receivers and earthquakes as the energy source, seismologists look at the Earth in a similar fashion. By using the arrival times from worldwide earthquakes, seismologists were able to define layers in the Earth. Later they expanded the method to look at smaller areas. Let's look at how this is done by using a highly simplified model of a uniform crust. For simplicity, we will use straight-line ray paths so the seismic waves won't get deflected and bent by different layers as they do in reality. An evenly spaced grid of seismometers records earthquake arrival times. Seismic waves travel through different materials at different speeds. By measuring the time it takes seismic waves to travel from an earthquake to different seismic stations, scientists deduce velocity variations within the Earth. Late arrival times for the slower ray paths in the shaded red area indicate slowing has occurred somewhere along the way. We won't actually know where the slowing has occurred until the data have been analyzed. By using what we know about how seismic waves travel through different materials, we can infer what the structure might look like. What does this tell us geologically? What are these anomalies? Well, they could be regions that have different compositions, temperatures, or fluid contents, including water, steam, or magma. In order to know which, seismologists work with other Earth scientists such as geologists and geochemists to combine independent observation to solve ambiguities.
Por aqui o outro era engraçado.
Era ali uma coisa.
Não, é ali, assim, de lado.
would you do if you have seconds to prepare for shaking from an earthquake that has already begun? More than 143 million people in the United States are exposed to potentially damaging shaking due to earthquakes. Most of our nation's earthquake risk is concentrated in highly populated areas on the active plate tectonic boundaries of the west coast of the continental United States. The U.S. Geological Survey operates the Shake Alert Earthquake Early Warning System, which is part of the Advanced National Seismic System. Shake Alert is not earthquake prediction, but a Shake Alert message issued by the USGS indicates that an earthquake has begun and shaking is imminent.
Don't let yourself be convinced to do something that you know is bad, and then even try to share it.
With even a few seconds of warning, Shake Alert can save lives and reduce injuries by alerting people to take a protective action such as drop, cover, and hold on. Shake Alert further protects people and infrastructure by triggering automatic actions, such as slowing down trains to prevent derailments, opening firehouse doors so they don't jam shut, and closing valves to protect water systems, and to stabilize equipment during life-critical situations. How does Shake Alert work? When an earthquake occurs, seismic waves carry energy in all directions away from the epicenter. P waves, similar to sound waves, move quickly through the ground, followed by the slower and generally more damaging S waves and surface waves. Sensors detect the seismic waves and send that information to a Shake Alert processing center, which requires that at least 4 sensors detect the earthquake. If the earthquake fits the right profile, the USGS issues a Shake Alert message. Distribution partners then produce and deliver an alert to people and trigger automated systems. Alert delivery can be before, during, or after shaking from S waves and surface waves. Alerts can be delivered to people through apps designed for cell phones and other wireless devices, over public address systems, TVs and radios, and by FEMA's Wireless Emergency Alert System, WEA, which is also the source of Amber Alerts. For every earthquake, there is a region near the epicenter where alerts will not arrive before shaking begins. That's because close to the epicenter, the P and S waves are too close together, and the Shake Alert system needs time, often just seconds, to estimate the earthquake's magnitude and shaking levels before issuing a Shake Alert message. That means that people close to the earthquake epicenter might not get an alert until after the shaking has already started. Those farther away from the epicenter could receive more warning time before shaking arrives. If an earthquake continues to grow in size, additional Shake Alert messages might be issued, updating the estimated magnitude and expected shaking for that event, which will result in alerts being delivered to a broader area. The USGS recommends that when you receive an alert, you should take protective action immediately. Do not wait for shaking to arrive. If you are near the coast in a tsunami-prone region, it's important to get to high ground quickly, but only after shaking stops. Before traveling to a new place, learn about both the local hazards and the recommended precautions to take by reading information found in the city, county, or state's emergency management websites. Knowledge of your surroundings and practicing protective actions are critical components of preparedness for any disaster. Always remember, if you receive an earthquake alert or experience shaking, drop, cover, and hold on until all shaking stops. Seismometers can detect anything that shakes the ground, from earthquakes to industrial noise to bombs. But how do seismologists tell the difference between, say, an earthquake and a large bomb exploding, when both release intense ground-shaking forces? Let's examine two methods that are used. The first will introduce compressive and extensional effects of seismic waves as they are reflected in focal mechanisms, and the second will show actual seismograms. When a bomb detonates, the concussive effect pushes seismic energy in the form of compressional P waves, similar to sound waves, in all directions away from the point source. Let's watch it in map view using springs to show the compressions. When the P waves reach each of the seismometers, they record an up signal, because the ground is bumped up as compressional first motions. An earthquake doesn't explode from a point, but by sideways slip on a fault plane. When the fault slips, it both pushes the rock ahead with a compressional force and pulls on the rock behind, resulting in an extensional force. Let's replay it using springs to show these compressions and extensions. The part of the fault moving towards the sensor causes a compressional first motion, and the part of the fault moving away from the sensor causes an extensional first motion, recorded as a down on the seismogram. This process means that seismic stations record both extensional and compressional P waves. If we represent compression with plus signs and extension with minus signs, we see that 2 quadrants are compressive and 2 are extensional. If we darken the compressive quadrants, a distinctive pattern called a focal mechanism arises. This pattern tells us that there was a horizontal strike-slip motion on this fault. A variety of patterns indicate whether the fault was normal, reverse, strike-slip, or a combination. In the case of the bomb, all regions of the pattern have pluses. Thus, it would be black in all quadrants. Distinguishing an earthquake from a bomb also requires a close examination of seismic wave patterns. We can show the difference between them by using pairs of seismograms from earthquakes and nuclear explosions that occur near each other. Because the seismic energy of an explosion pushes outward equally in all directions, the result is strong P waves and weak S waves. In contrast, the rapid sideways motion of an earthquake typically produces weak P waves, and because of that shearing motion, it generates strong S waves and surface waves that are of higher amplitude and slower, thus they show up later. In summary, the two principal methods to discriminate between an explosion and an earthquake are by using their seismograms and by their focal mechanism.
Então, tiveram clientes?
Não. Estive aqui a pôr uns filmes muito bonitos.
É, pronto. Aproveitamos.
Viste aqui o Shake Alert. Eu pus outra vez o Shake Alert porque a Inês estava a dizer que não tinha som. Aquele Shake Alert é muito giro. Não, foi quando foste lanchar, não viste?
O quê?
O quê?
Ver o quê?
O Shake Alert.
O Shake Alert? Que é
o Shake Então, é aquela coisa, como é que se diz? App para o telemóvel que te diz quando é que vem lá o sismo.
E como é que isso se chama?
Shake
Alert. Está bem, o alerta, está bem, Shake Alert.
Não viste?
Não.
Não, é giro, é giro. Já pus 2 vezes, quer dizer, também posso pôr porque os espectadores. Queres ver agora? Posso pôr de novo.
Estou a preparar aulas, agora estou a preparar aulas.
Está bem. Estava aqui sismo ou bomba. Também já pus sismo ou bomba.
Ainda vi um bocadinho, sim.
Deixa eu ver o que é que há aqui mais interessante. Há aqui vários engraçados, só que eu não vi todos, portanto não sei. Não. Diferença.
Vi um muito engraçado sobre ressonância, mas agora não o consigo descobrir.
Mas aquele com o edifício. Já sei.
Tinha com aquela ponte, aquela selva de ponte.
Sim, já vou buscar.
Era engraçado esse.
Sim, não, eu ainda há bocadinho vi. Acho que está aqui. Isto é a liquefação. Acho que está aqui na última página, no 7. Não, 7 são vulcões, deve estar no 6. Eu até ouvi ontem, por acaso, esse. Também. Também não está a aparecer. Até apareceu pronto, a experiência que nós fizemos com o skate.
Exato, é isso mesmo, era esse mesmo.
Eu vi-o ontem. Eu vi-o ontem e já passei por ele hoje. Mas não sei se eles mudam de sítio. Tinha posto aqui umas cábulas, mas eu acho que eles não estão no sítio onde eu tinha pensado que estavam. Pois, é estranho. Está aqui. Eu vou pôr. Vou partilhar.
Boa.
Já encontrei. Peço desculpa, vou pôr da ressonância.
To understand the resonance of buildings during earthquakes, we will look at other resonance systems. The natural frequency of a swing makes it easy to maintain the motion using little energy. A prolonged wind swung the bridge on the right at its natural frequency until it exceeded its structural integrity and tore apart. The frequency of a wave refers to the number of waves that pass through a point in 1 second. A period is the amount of time that it takes one to pass the given point. A frequency of 1 cycle per second has a 1 second period. If the frequency doubles to 2 cycles per second, the period is only half of a second. Resonance is a tendency of a system to oscillate with greater amplitude at some frequencies than at others. The resonant frequency of any given system is the frequency at which the maximum amplitude oscillation occurs. For example, the resonant frequency of the 1 meter long pendulum is 1/2 of a hertz. If the string were 1/4 of the length, it would vibrate at twice the frequency. Small amplitudes can be approximated by this equation using length and the gravity constant. Resonant systems can be used to generate vibrations of a specific frequency to create music. Strings under tension, such as with this cello, have resonant frequencies directly related to the material of the string, as well as the mass, length, and tension of the string. The mass of the slow C string resonates at 264 Hz, whereas the thinner A string of a different material resonates at 440 Hz. Now, we use a simplified analogy of boats at sea. A series of waves, particularly when they hit broadside, can initiate rolling behavior. The smaller boat is affected by short-period low-amplitude waves that slap against the ocean liner with no effect. Small boats, on the other hand, will ride up and over long-period high-amplitude waves as the larger boats begin a long, slow rock. Now, let's look at how buildings are affected by earthquake-induced seismic waves. All buildings have a natural period, or resonance, which is a number of seconds it takes for the building to naturally vibrate back and forth. The ground also has a specific resonant frequency. Hard bedrock has higher frequencies than softer sediments. If the period of ground motion matches the natural resonance of a building, it will undergo the largest oscillations possible and suffer the greatest damage. Small buildings of 1 or 2 stories resonate naturally at much less than 1 second periods. A 1 second period will affect buildings of about 10 stories. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story building resonates at a period of 5 seconds. During the 1985 Mexico City earthquake, the ground beneath the city resonated with a 2-second period for over a minute. Thus, medium-height buildings with similar natural periods suffered the most damage, while short, old, weak stone buildings and skyscrapers were relatively undamaged. That proved to be what is called a resonance disaster, which is how engineers describe the destruction of a building by seismic vibrations at a system's resonant frequency. It is because of prolonged energy input that the system swings more and more strongly until a structural load limit is exceeded. A key point here is that small buildings on hard rock and large buildings on soft sediments may suffer more damage and ground motion effects from an earthquake than small buildings on soft sediments and large buildings on hard rock. Resonance is one factor that contributes to earthquake damage. Of equal or greater importance are building design and the quality of construction materials. By determining the resonant frequency of the ground beneath the building site, the building design can be modified so that a resonance disaster does not occur. The following demonstration shows how to model resonance in the classroom.
The idea of the BOSS model is that different height buildings will respond to different frequencies of horizontal ground motion. A tall building will respond to very slow or low frequency oscillations of the ground. So if I move the base slowly back and forth, I can get the tall building to oscillate, where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, you need to move the base very briskly back and forth and dial in to the natural frequency of the short building, and we can see that the intermediate and tall buildings are barely moving.
House built on a weak foundation will not stand, oh no. Stories told through all creation will not stand.
Gostaste, Luís? Não sei se ele viu.
Quem é o Luís?
É o meu colega Luís. Da faculdade. Mas deve ter ido lanchar. Havia aqui outro engraçado. Onde é que façam?
Enviei agora uma mensagem para si. Esse de ressonância é que era bom para o Luís.
Desculpa, a ressonância aqui é?
Mandei aí uma mensagem para si. Também é sobre ressonância, mas é sobre modelozinhos. Isso é que o Luís ia gostar. Aqueles modelos que ele faz com os edifícios.
Sim, mas isso é o que apresentou este professor aqui.
Não,
ou não?
Não, é diferente.
Espera, deixa-me só que estava aqui a pensar uma coisa que me perdi. Espera um bocadinho, ver se eu consigo. Ok. Deixa eu ver se eu consigo encontrar aqui um engraçado. Eu já vejo a mensagem. Estou aqui à procura.
Não se preocupe.
Estou aqui à procura de um que eu também tinha visto ontem, engraçado, tomei aqui nota. Ok, já vi.
Ó Paula.
Sim.
Eu vou ter que ir embora.
Sim. Eu deixo lá. Pois, fica aqui eu e o Luís e logo se vê.
A Liliana, não é?
A Liliana ainda não falou, portanto não sei se está ou se está só a fazer número.
Já estou.
É como o Ricardo. A Liliana, já estás?
Já. Fui só ali à rua com a cadela, mas já voltei.
Mas nunca sabe. O Miguel só está aí a fazer número, não é, Inês?
O Miguel não está lá, mas não está. Deixa o computador. Aliás, eu estou a ver aqui o computador, eu tenho aqui o computador ao lado.
Está marcado.
Para ir vendo o Zoom ao mesmo tempo que estou a ver o
YouTube.
O YouTube.
Está bem. Pois, não, mas pronto, está bem. Então, mas tu mandaste aqui, não percebi bem, desculpa lá, este link era sobre?
É sobre ressonância, mas é um senhor com os modelos, mas com aqueles modelozinhos de pequeninos.
Já sei. Mas estava a dizer que só mandaste para mim, não mandaste para o Luís.
Pois não.
A não ser que mandaste reservadamente também para ele.
Não.
Então, se a gente abrir, ele começa a funcionar?
Experimento. Faça a mesma ideia.
Vou experimentar.
Fazer um copy-paste.
Sim. Começa. Espera lá, que eu vou compartilhar então. Onde é que está? Acho que ele já está a falar. Está sem som.
And what kind of problem is, it's when we see this kind of picture, it's a Mexico earthquake, we see that small buildings
É isto, não é?
É isso.
Collapse and not high buildings. So it's a real problem. And what kind of problem is? It's a problem of resonance. So buildings resonance. So to understand this phenomenon, we can make this experiment with the same screwdriver, automatic electric screwdriver, with an eccentric here. And this system we can switch on, off, and also increase the speed. We have different building of different height, and I'm going to make the system working to show to understand what is the resonance phenomenon. So with this system, I can increase the speed and nothing appears because the eccentric is not far from the axe. So now I am putting this far, and now I see the beginning of the working, this system working. So now I'm going to study the resonance. We can see that the big buildings resonates. I'm increasing the speed. And now, yes, the big building, and now the intermediate building resonates. And I increase again, and I see the small building resonating too much and no foundation. So small buildings collapse. Maybe exactly like that, but it's not a problem of foundation. Here is a problem of size of building. So to change resonance frequency, it's possible to prevent resonance. To put a big mass on the building like that, and so the building does not resonate anymore, and I can search the new resonance because building is going to resonate, but in a low frequency like that. So the new frequency of resonance is this one. To prevent resonance, it's also possible to put a big mass, and the building resonates at low frequency. As you can see, the big mass is fixed, and the building has a big resonance. So now I'm going to make the mass free. We run in removing the scotch here, and when the mass is free, the system is an amortissement, and as you can see, the mass moves, but not the building. So it's the system which is used in Taipei Tower, and the computer are pushing the big mass to prevent the resonance of this building.
Bem.
Bom, meninas, agora é como vou embora.
Era lá, deixa-me desinterromper, só para dizer uma coisa. Não sei se alguma de vocês estava uma sísmica onde eles fizeram um concurso. Ah, bem, agora esta porcaria ficou aqui a funcionar, espera lá. Ok. Houve uma sísmica onde eles fizeram um concurso para ver, não sei se foi nos Açores, acho que foi nos Açores, a última dos Açores. Houve um conjunto de estudantes que construíram uns edifícios e depois eles botaram numa mesa sísmica, um estilo de uma mesa sísmica que eles tinham para lá pequenina, para ver qual é que resistia melhor. Depois levou um prémio aquele que resistia melhor. Mas acho que foi na sísmica, sim, penso que sim. Mas de qualquer modo isto é engraçado, sim senhor. Muito obrigado. Muito obrigados.
Pronto, olha, resto uma boa noite.
Obrigada. Bom fim de semana, bom feriado, etc.
Exato.
Eu e a Liliana ainda temos trabalho na segunda-feira, não é? Mas a Inês faz ponte.
Tá, beijinhos.
Ok, beijinhos, tá.
Beijinhos.
Eu já falo com a Liliana, deixa cá eu pôr aqui. Ok. Bom, estamos cada vez mais.
Ah, sim, está emocionante.
Olha, hoje era para ter enviado um mail, ainda vou enviar. Há bocadinho apareceu aqui uma pessoa, um rapaz, que apareceu fotografia.
Sim, desapareceu.
Depois estava a passar um filme, entretanto pensei se ele ficar até ao fim, pergunta qualquer coisa. Mas depois ele até acho que ficou um bocadinho sem filme, mas não disse nada. Apareceu sem som e sem imagem, não sei.
Pois.
Quer dizer, eu estou a dizer que é um rapaz que via fotografia, não é?
Sim.
Pronto, o que é que eu ia dizer? Vou mandar um mail a ver se a reunião pode ser às 3h30, a da segunda-feira. Pronto, porque tenho aí um problemazito às 2 e depois tenho medo que não consiga estar a tempo, e 3h30 já estou, como já estamos na altura em que a gente não pode sair de casa, às 3h30.
Exato.
Eu eventualmente às 2 vou ter que ir à rua. Portanto, ficava um bocadinho mais descansada, para não ficar aí muito estressada. Se o Rui puder, eu vou mandar um mail. Tu podes, não podes?
Sim, eu posso sempre. Agora não posso sair.
Estás confinada. Pois é, ele pode é ter outra reunião, não é? Portanto, não é o teu caso. E eu assim ficava um bocadinho mais descansada, porque eventualmente às 2 vou ter que sair e depois tenho que voltar antes das 3, é verdade, mas não sei se volto antes das 2h30. Ou, enfim, em princípio voltar às 2h30 ou perto disso. Mas pronto, era para eu ficar um bocadinho mais descansada. Okay. O Luís vai-se embora e volta às 8. Está bem, ok. Então ficamos ao nossas turmas.
Boa viagem.
Boa sorte. Obrigada. Ele está a dar isto para mim, vou ter obrigada. Está-me a desejar boa sorte. Espera. Pronto. Não é para a Inês que eu queria mandar, era para o Luís. Aqui, Luís. A Inês já se foi embora. Está bem. Pronto, o Luís diz que outra reunião, mas aparentemente ficou com o computador ligado, como o Miguel.
Agora já se foi embora também.
A gente pode ir fazendo podemos já ir adiantando a reunião.
Pois, exato, para este andar.
Consegues pôr isso tão bonito? Tu pões algum ecrã no fundo? Porque,
não, eu só pus a imagem.
Depende da definição também do computador, não é? Do vídeo do computador.
Provavelmente, e da câmara, sim.
A Susana também disse que... Eu disse, o que é que tens atrás de ti? Só tralha. Porque ela geralmente está no sótão e realmente aquilo... Sim, não é assim... Eu vou até algum pano... Perdão. Tens algum pano verde? E ela disse que era só tralha. Portanto, ela geralmente está no sótão, que quando se vê atrás está no sótão. E eu tenho aqui esta parede branca e depois aqui estes quadros, não é? Posso fazer também, olha, ressonância. A começar, se eu desaparecer é porque colapsei, assim. Entrei em ressonância. Mas pronto. E ela também estava bem, mas o meu não, o meu fica com assim, aparece-me aqui os encarnados no meio da cara e não sei o quê.
Isso tem a ver com a definição da câmara.
Pois ele diz qualquer coisa que o vídeo não é bom, não sei, diz qualquer coisa. De maneira que, pronto. Agora, a gente tem que estar aqui até às 8, não é?
Pois, exato.
Tu estás até às 8, é? Das 6h30 às 8, é isso?
É.
Ainda temos... Vá lá, eu já só tenho meia hora. Lanchar. O meu marido já está a lanchar, mas eu não. O Luís também disse que ia lanchar. Enfim, mas... Pois a Inês estava com medo que não aparecesse ninguém, e pelos vistos não apareceu, não é? Mas eu estava com mais medo porque ela disse que de vez em quando aparecia assim uns infiltrados e que faziam coisas más. E eu estava com medo. Ela disse que já lhe aconteceu, passei de filmes pornográficos. E eu disse, se aparecer nem dou por isso. Ela disse, dá. Como isto é aberto, e
pois.
Não sei, felizmente nunca me aconteceu, porque eu disse também, ela disse, a primeira vez que aconteceu eu fiquei tão feliz, eu desliguei aquilo tudo. Eu disse, também se me acontecer, também desligo tudo.
Claro, exatamente.
Mas pronto, e de maneira que não sei, mas felizmente, pronto, isso eu tinha mais medo disso do que não aparecer ninguém. Não aparecer ninguém é um bocado chato, mas pronto, olha, mas passa. Se fosse isso era pior, para mim era pior, porque sim. Só de sentir que a pessoa está invadida, não é? Portanto, enfim... Sim. E depois, claro, podia estar outras pessoas a verem e eu acho que não vou gostar se vir.
Exato.
Pronto, o problema é a pessoa estar a dirigir a reunião e depois aparecer aquilo, não é?
Claro. O problema de ser online é que as pessoas podem escolher e então, quando é lá no museu, o circuito está feito e as pessoas não é obrigadas a passar, mas acabam por ter que passar em frente ao sítio. E aqui não.
Deixa só ver. Espera, é que agora estou a ver a minha cara é que está a passar tudo
no YouTube, sim. Exato.
Eu espero é que não fique gravado.
Pois, não sei.
Bom, também não estou a dizer assim asneira nenhuma, mas de qualquer modo não era bem para sei lá, para o relatório do NEI.
Mas...
Enfim, pronto, está bem. Eu esqueço-me desses pequenos detalhes. É que isto pode estar outras pessoas a ver ou a ouvir e pronto. Porque, bom, quando é aos nossos também, só que nós só mandamos o link para nós próprios, não é? E pronto. Então não podemos fazer a nossa reunião ainda.
Não pode ser. Então fica toda a gente a saber.
Então só se eu passar mais uns filmezinhos para entreter.
Sim.
Posso ir passando os filmes. Estes filmes são da Iris, esses são engraçados. Eu ontem vi alguns, mas não vi todos. E alguns engraçados. Tinha visto, por acaso, esta ressonância tinha visto. E aquele que a Inês passou ao princípio, eu também acho que eu vi. Não sei se foi a Susana que mandou um link separado, que não é da Iris, porque era o da aparece o Sismo 1906 de São Fernando e sim. Também é sobre a intensidade e magnitude, também vi para aí, mas agora estava aqui à procura no Iris e não o vi. Deixa cá ver se vejo aqui algo interessante na Iris que eu tenha visto ou que eu não tenha visto. Este de liquefação não é os mais interessantes, mas também podemos passar de liquefação. Pode ser que haja pessoas que, entretanto, se liguem e gostem de ver. Vamos passar um de liquefação. Isto só demora 45 segundos, é muito rápido. Bom, vamos lá. só tem 45 segundos, mas é engraçado.
É giro porque é passado no século passado. Casa da música e do carrinho.
Então, tu dizes isso, porque realmente nós já somos, quer dizer, nós, a minha geração, somos muito velhos, já nascemos no século passado. A minha avó...
Eu também nasci.
Pois, a minha avó nasceu em 1898, 88, ou lá que era, eu dizia, século passado. Não. Também agora os meus netos todos já são deste século. As filhas não, mas os netos são deste século. Portanto, quando é assim o século passado, parece que é assim. O século passado para mim ainda é 1800. Em relação ao século que eu nasci.
Sim.
É, sim. Tá bom, então deixa lá ver se há algo mais engraçado, outro engraçado. Ele vai repetir, não era isto que eu queria. Deixa cá ver o que é que ele tem, o que é que há aqui engraçado. Alguns eu não cheguei a ver, deixa cá ver que... Aqui uns sobre tectónica, que depois podes passar tu.
Já tenho aqui muitos abertos também.
Os teus é sobre quê? Hein?
É um bocadinho de cada. Eu até fiz uma apresentação toda catitas.
Pois, eu não fiz, eu compilei algumas figuras só, mas pronto, mas... Este aqui pensava que era mais engraçado, é aqui do movimento das placas, pensei que era mais engraçado, mas não é grande coisa. Deixa eu ver se há aqui outro. Já agora vou ver este liquefação, a ver o que é que ele diz. Este não vi. Isto é mais rápido, 27 segundos. E não tem música. Este não tem som, é mesmo assim. Acho que vi. Agora que eu estou a ver, acho que vi sim. Mas como era assim, não sei assim. Esta imagem é de loma preta, assim, já conhecia. Esta imagem tem uma fotografia que às vezes mostro nas aulas. Ora, então vamos lá ver outro. Fotografia já mostrei. Eu também a primeira pessoa, não sei se estavas quando a Susana esteve a falar.
Estava.
Depois também uma pessoa que falou em previsão.
A medical doctor recently asked why seismologists, with all their modern tools, can't predict earthquakes. What if he, also a scientist, considers predicting the heart attack of an obese 50-year-old smoker with a family history of heart disease and high blood pressure? By using the patient's history, lab data, and stress factors, cardiologists can generate a probability for having a heart attack by a certain age. But they cannot predict the date, location, or magnitude of the attack. And then there's the healthy young patient with none of the previous known risk factors who suddenly has a heart attack. Earthquakes can also be seemingly unexpected. Seismologists would love to be able to predict a major earthquake. However, they can't define a specific time, location, and magnitude of an earthquake, which are all required for a prediction. By using a wide array of monitoring techniques, incorporating new data on active faults, and gaining an improved scientific understanding of how faults rupture, seismologists are able to narrow down the probabilities and thus forecast the likelihood of a quake in an area within the next so many years. From those long-term rates, human risk can be assessed by taking into account hazards due to population density, man-made structures, weak building materials, and more. Rather than trying to accomplish short-term predictions, the USGS focuses its efforts on long-term mitigation of earthquake hazards.
Gostaste? Pequenino. Sim. Não, não era isto que eu queria. Era aqui este. A ver, isto é para a gente, para nós aprendermos.
Ever wondered how to read the data on a seismogram? The Webicorder is the digital version of the paper records used by scientists in days of yore. Seismometers measure vibrations. More vibration, more wiggle. Some seismometers measure only up and down. Sometimes they shake too much and the data are off scale. Some seismometers record in all three dimensions. Many Webicorders display 15 minutes per line, alternating colors as time passes. Plots are automatically updated every few minutes. Scientists use Webicorders for a quick look at current activity, but Webicorders are really just a blurry picture of the actual data. To really understand what's going on, they look at the real data, which is far more informative. Here's a small earthquake. It begins as a sharp crack as the rock breaks, and then quickly decays with time. In this plot, the data are clipped to allow viewing of other data. This can be very useful when there are lots of earthquakes, as in this seismic swarm with multiple earthquakes of magnitude 2 or 3. Seismometers are sensitive enough to pick up vibrations from earthquakes around the world, if they're big. This is what the giant 2011 Japan earthquake looked like on a seismometer in Wyoming, 5,000 miles away. Compared with the P and S waves that travel through the Earth, surface waves are slower and arrive later, but can continue to be recorded for hours as they propagate around the Earth. Seismometers not only record earthquakes, but anything that makes the ground vibrate. Helicopters, ocean waves, traffic, animals, and wind. Wind can be seen as noisy periods. Here, the wind picks up each day and drops off at night. Here, traffic noise shows up on a seismic station located a quarter mile from a road. Seismometers are sensitive electronic instruments, often deployed in harsh wilderness environments. They can, and do, break. Sometimes they just stop working, but sometimes they just become noisy and unreliable. Here's a record from a 3-channel instrument, one of which is broken. Guess which one? Nearby equipment and machinery can also create interference. Worried about something on a Webicorder? Then check readings from nearby instruments. Anything that shows up only on a single seismometer is either noise or earthquake activity too small to worry about. Okay, you've done your homework and you're ready to graduate from the Acme School of Webicorder Arts and Sciences. Congratulations! Now you're prepared to start cruising data on the internet. Have fun out there, mind your P's and S's, and keep in mind, if you see an ominous signal at Mount Scarymore, don't hesitate to seek the opinion of a professional site.
Parou a meio. Porquê? Não sei porquê. Parou. Ok. Não foi até ao fim, mas não sei porquê.
Não sei.
Ora, então vamos aqui a ver outro. Este aqui, este não tinha visto. Este aqui... Vamos aprendendo coisas. Pode ser que eles nos ensinem alguma coisa. Ainda estás a ver o ECA partilhado, não estás?
Estou.
Eu não descompartilhei. Não está a andar. Agora está. Este não tem som? Este não está com som. Também para as relações ambientais. Ok. Como é que ela se chama? Eu não estou a lembrar do nome dela, aquela que trabalha com o Luis Matias nas baleias.
Andréia.
Andréia, preparou um quiz, viste? Chegaste a ver?
Não.
Preparou um quiz aqui, portanto, para adivinhar que som era aquele. Era baleias, depois já também tinha um barco, já não sei se tinha também animais ou assim uma coisa qualquer. Quer dizer, animais sem ser baleias. Pronto, eu tinha mais de 2 ou 3, mas a maior parte deles era baleias, não era a baleia maior, até era a baleia mais pequena, enfim. Mas, então, é também para adivinhar com o som e o sinal o que é. Portanto, o som, sim, acho que tem um som associado ao sinal, acho que sim, qualquer coisa assim. Mas eu achei difícil, eu cá não acertei. Não, porque não é assim tão nítido. Portanto, já não me lembro bem como é que era, mas não é assim tão nítido. Deixa cá ver. Estava aqui a ver que também havia aqui um que eu gostava de ver e que não vi ainda. Para mim encontrá-lo. Tem a ver o que é que eles dizem aqui das sombras, já agora.
A seismic shadow zone is an area that does not receive direct body waves. The P wave shadow extends from angular distances of about 103 to 140 degrees from an earthquake due to refraction at the core mantle boundary. The S wave shadow which results from S waves being stopped entirely by the liquid core, extends from 103 degrees. So what does a seismograph record in the shadow zone? First, we look at just the direct and surface wave arrivals to two seismic stations, one outside the shadow zone and one inside the shadow zone. An earthquake sends P and S body waves through the earth. The direct P and S waves arrive at the station outside the shadow zone. Only highly sensitive seismometers can detect these. The houses merely depict direction of motion. In the shadow zone, you'll notice there are no direct P or S arrivals, but the slower surface waves show up at all stations. An actual seismogram at 92 degrees shows the arrival of the direct P and S waves as well as the surface waves. However, if we look at an actual seismogram from 106 degrees, we see more complexity than just the surface waves we expected. So what's going on inside Earth to explain the arrival of seismic energy recorded by seismometers? Because we're familiar with the wave properties of light, let's use that experience to help us understand seismic wave behavior. Objects blocking direct sunlight cause light shadows on the ground. However, our experience tells us that these shadows are not absence of light. If the tree in the house blocked all light, the shadow would appear black, and if we entered the shadow, we would see nothing. But most shadows aren't black. That's because light reflects off nearby objects, and the redirected and reduced light energy strikes and brightens the area in shadow. Light can also bend. For example, refracting at the water surface, illuminating objects below the surface, or appearing to make half-submerged objects bend. Like these shadows on Earth's surface, the seismic shadow zone is not an absence of seismic energy. Here we see P waves encountering boundaries and being redirected into the seismic shadow zone. For example, some energy is reflected off the surface and continues its curving path through the mantle. Other energy skirts along the core mantle boundary and is diffracted back to the surface. Still other waves refract at the outer core mantle boundary and reflect off the outer core inner core boundary on their way to the station. When we compare this to the actual seismogram, we see that the arrivals are due to these reflections and refractions, therefore revealing that seismic energy does arrive in the shadow zone, but through an indirect path. Let's take a broader view to arrivals at all distances from the epicenter. Body waves reflect, refract, and diffract at boundaries throughout the Earth, creating a complexity of arrivals at all distances. This complexity permits us to learn incredible things about the dimensions and properties of the deep Earth.
Amen. É engraçado. Há aqui um que eu mostrava nas aulas sobre os tipos de sol, e depois deixei de o ver, mas havia aqui um sobre o Monte Santa Helena, que eu gostava de saber, eu gostava de ver porque não conheço bem aquilo. Se calhar é na parte da geologia. Eles têm aqui uns mais virados para a geologia, tectónica, não sei o quê. Himalaias. Isso eu não sei se eles mudam, porque eu ontem vi uns que agora não encontro. Esta aqui do Alasca. As presas. Ressonância. Este é o que eu costumo... Eu conheço este, que eu estava nas aulas.
Sim.
Tem a ver com o tipo de terreno. E aqui. que havia ali que fação. Deixa eu só ver aqui a ressonância, portanto, a ressonância. Aqui. Aqui no Newmazi também foi um sítio onde houve um grande sismo. E, quer dizer, sim. Foi no 40, será? Do século passado. Também tem aqui umas intrusões magmáticas. Não me diz nada este. É que a geologia tectónica, não sei o quê.
Seismic hazard is the probability of ground shaking due to earthquakes. And
eu vou para os geólogos.
The scenic features of the Cascadia subduction zone result from the subduction of the oceanic Juan de Fuca plate beneath the continental North American plate. Major geomorphic features formed by tectonic deformation, volcanism, and erosion are visible in the topography and bathymetry of the region. The dense oceanic plate, created at the spreading center, subducts beneath the more buoyant continental plate at a rate of 1 to 2 inches per year. During the collision, the leading edge of the continental plate is pushed eastward, deforming the rock. At the same time, sediment and rock are scraped off the top of the oceanic plate by the continental plate and accumulate along the boundary. As the eastward moving oceanic plate shoves the edge of the overriding continental plate backwards, the leading edge of the continent buckles parallel to the boundary, forming the coast range, a belt of uplifted land. These are not volcanoes. The stunning peaks of the Cascade Mountain Range are composed of volcanic rock and their granitic roots. They form a line because at this location, about 150 miles east of the plate boundary, the oceanic plate has descended to 44 miles below the surface. At that depth, the oceanic plate sweats off its volatiles, mostly water, which migrate upward. These volatiles lower the melting point of the mantle rock, forming hot magma that rises toward the surface. Caught in the crunch between the Coast Range and the Cascades is this valley, a sediment-filled, fertile region, home to the most populated communities of the Pacific Northwest. Understanding the geologic features also necessitates an awareness of its hazards, such as volcanoes, earthquakes, and landslides that shape the landscape.
Este aqui é aquele vulcão do Monte Santa Helena. Ok. Por acaso não sabia que estava ligado a esta Cascade Subduction Zone. Cascadia. Vamos ver o que é que ele fala aqui das forças. Oi, isto é grande.
This is the big picture.
O que segue passar?
We once thought that mantle convection below the tectonic plates could drive plate motions. Early textbooks showed mantle convection cells, like in a beaker of hot liquid on a Bunsen burner, pushing plates along from below. Current dynamic models have plates moving as part of a gravity-driven convection system that pushes young hot plates away from spreading ridges and pulls old cold plates down into subduction zones. Remember that lithospheric plates, also called tectonic plates, have a layer of crust on top of lithospheric mantle, the outermost rigid part of the mantle. These move as a single unit. The hotter asthenosphere beneath the plates is solid but less rigid mantle rock that can slowly flow. Now let's look at the broader picture. This map shows how the seafloor increases in age with distance away from spreading ridges, such as the East Pacific Rise or the Mid-Atlantic Ridge, where new ocean plate is forming. Spreading ridges stand 2,500 meters higher than deep ocean basins. At a spreading ridge, the ocean depth is only about 3,000 meters. Ocean depth increases with age of the underlying plate, so that where the plate is more than 80 million years old, the overlying ocean increases to 5,500 meters deep. Let's examine the formation of new oceanic plate and how that plate cools with age. As hot mantle rock rises to lower pressure, a small portion of this upwelling asthenosphere melts to form magma that builds the 7-kilometer thick oceanic crust at the edges of two diverging plates along the ridge axis. Beneath the crust at the spreading ridge, there is only a thin layer of lithospheric mantle because it is unusually hot in the upwelling zone. This hot, and therefore lower density mantle rock, supports the 2,500 meter elevation of the spreading ridge. As the plate slowly moves away from the ridge, it cools by conducting heat through the crust to the cold ocean water above. At the same time, the underlying asthenosphere cools and adds to the bottom of the lithospheric plate. Thus, although the crust maintains its thickness during migration away from the ridge, the lithospheric plate thickens and cools to create ocean basins that extend 5 kilometers in depth. A simple way to think about elevation is that the plate is young, hot, and high at the spreading ridge and becomes old, cold, and low during the aging and cooling process. Mathematical modeling of this cooling process illustrates the ocean plate becoming cooler and thicker with age. The temperature at the bottom of the plate is about 1,300 degrees centigrade. Notice that most of the cooling process occurs between age 0 at the ridge and about 80 million years when the ocean plate has grown to about 100 kilometers thick. The upper plate is less than 600 degrees centigrade, thus is the only part of the plate cold and brittle enough to fracture and produce earthquakes. Though still rigid, the lower plate is warmer and can deform in a ductile or plastic fashion. So what force pushes oceanic plates away from spreading ridges? Any mass on a slope is affected by gravity, seen most dramatically with avalanches and landslides. Spreading ridges are broad, undersea mountain ranges, and although the flanks of a spreading ridge are a relatively gentle slope, the mass on that slope is humongous. The force of ridge push is 0 at the ridge, but increases quickly with distance and age, pushing the cooling and thickening oceanic plate away from the ridge. Now what about slab pull? We'll consider a 30 million year old oceanic plate, which we'll call a slab, subducting at 5 centimeters per year into hotter asthenospheric mantle beneath a continental plate. As the oceanic plate subducts, the warming process takes many millions of years as the slab descends. The deeper part of it is continuously replaced in a conveyor belt fashion by a cooler plate from above. Mathematical modeling again illustrates the temperatures within the subducting oceanic plate. In this example, lithospheric mantle rock in the subducting plate at 150 kilometers depth is 1,000 degrees cooler than the asthenospheric mantle at the same depth. The cooler temperatures mean that the density of rocks in the subducting slab is greater than the density of the hotter asthenosphere. While gravity pulls down on all rocks, it pulls down harder on more dense rocks. This enhanced gravitational force on the cooler and denser rocks in the subducting plate is the slab pull gravity force. Earthquakes, including great megathrust earthquakes, occur on the shallow part of the boundary between the converging plates and within the shallow parts of both plates near that boundary. In addition, there is a zone of rock cooler than 600 degrees Celsius within the subducting plate that remains brittle and within which earthquakes can occur to depths of hundreds of kilometers. Observations of intraplate earthquakes and other indications of stress with tectonic plates suggest that the slab pull force is usually larger than the ridge push force. It is noteworthy that fast-moving plates, like the Pacific Plate, generally have a fast spreading ridge pushing on one side, while the subduction zone pulls on the other side. In this big picture view, we see that lithospheric plates are part of a planetary scale thermal convection system. The energy source for plate tectonics is Earth's internal heat, while the forces moving the plates are the ridge push and slab pull gravity forces.
Ok. Bom, acho que está na hora de vermos a tua apresentação. Já agora? Já agora está na hora de passar a pasta, não é?
Pois, exato.
Pronto. Então, então mostra lá, depois também tenho que ir, depois não ficar aqui um tempo sozinha, depois posso ir e voltar, eventualmente, pronto, se estiveres aqui sozinha, mas já agora mostra lá a tua apresentação, para a gente ver.
Ora...
Portanto, vou aqui parar.
Não sei se isto vai funcionar, mas... Okay. Está a mexer?
Sim, gosto do título. Tens que pôr o ecrã grande, que é para se ver melhor.
Eu já pus.
Ah, está ecrã grande. Ah, sou eu que não tenho ecrã grande. Então, espera, não tenho ecrã grande no Zoom. Ok, agora sim.
Okay.
The exact epicenter. They've been in contact with the National Earthquake Center in Golden.
News reports commonly refer to an earthquake's epicenter. The word is a concept coined by Robert Mallet to help people visualize an earthquake's location. The epicenter is the map location on Earth's surface, above where the earthquake began. An earthquake actually begins inside the Earth at the hypocenter. The hypocenter ranges from several to hundreds of kilometers below the epicenter, in Earth's outer brittle layers. What do we mean by the earthquake begins? Let's place a grid on the strike-slip fault surface. A small earthquake releases energy at its hypocenter, suddenly, like a blast of TNT.
Centro, a zona do sismo é sentido com maior intensidade. Geralmente, corresponde geralmente. Se a falha for inclinada,
a magnitude 4 typically ruptures about 1.
Isso mais ao lado.
A magnitude 6 ruptures about 100.
Corresponde geralmente.
Often, there is no surface faulting at the epicenter, but if an earthquake is shallow and the rupture area grows vertically, it may offset the ground surface or create a fault scarp. All earthquakes, including the largest earthquakes like this one on a subduction zone fault, began at the hypocenter. Seismic and heat energy are continuously released as the rupture spreads, as though it were unzipping the rough surface of the fault, sticking and slipping during the chain reaction. The earthquake stops when the fault stops slipping. Computers can make
Supostamente era se fosse para responder a questões, não é?
Pois.
travel a curving path through the Earth, arriving at seismic stations from below. Compressive motion of the P wave is in the direction the wave travels, thus the motion of the seismometer will be mostly vertical with little horizontal motion. The S wave has a shearing motion perpendicular to the wave path, thus the S wave produces chiefly horizontal movement. Surface waves travel in an undulating pattern across the surface of the Earth, producing up, down, back, forth, side-to-side motion. The seismogram merely depicts motion, not direction of motion. The movement of the building is exaggerated to show the relative motion of each wave, only detectable by seismometers at this distance. If the Earth had no changes with depth, seismic waves would travel straight paths. But the Earth has composition, density, and temperature changes that cause the seismic rays to refract as velocity in the mantle generally increases with depth. We can zoom into a shallow part of the crust to watch how waves behave when crossing into boundaries of higher velocity. We will track two paths from an earthquake.
The direct path travels to station X through the slowest layer. The outer path continually refracts as it crosses boundaries of increased velocity until the incident ray reaches a critical angle and begins sending a head wave to the surface. These head waves return to the surface, refracting back at the same angles and velocities that they descended with. This is because they follow Snell's law at each boundary, with relative velocities now decreasing upward. Some of the critically refracted waves reach station X and beyond before the blue direct wave, which took the shortcut. This is because the velocity increases were great enough to overcome the slower direct path. The dashed black line emphasizes how much the wave is refracted in each layer.
Body waves from distant earthquakes travel a curving path through the Earth, arriving at seismic stations from below. Compressive motion of the P wave is in the direction the wave travels, thus the motion of the seismometer will be mostly vertical with little horizontal motion. The S wave has a shearing motion perpendicular to the ray path, thus the S wave produces chiefly horizontal movement. Surface waves travel in an undulating pattern across the surface of the Earth, producing up, down, back, forth, side-to-side motion. The seismogram merely depicts motion, not direction of motion. The movement of the building is exaggerated to show the relative motion of each wave, only detectable by seismometers at this distance.
The concept of a seismic shadow zone as a global effect of an earthquake is an oversimplification that ignores a broad array of refracted, reflected, and diffracted seismic waves that propagate through the Earth. For now, we'll just focus on direct, compressional P and shearing S waves. These are the body waves that take the most direct routes within the Earth and do create shadow zones, which are useful for teaching Earth structure. An earthquake, depicted here at the top of the globe for convenience, sends compressional P waves in all directions, refracting along boundaries with depth, causing curved paths. At the core mantle boundary, they are refracted or bent inward and slow down in the liquid. It's this refraction that causes a shadow zone between the angular distances from 104 to 140 degrees from the earthquake. S waves travel along the same path as the P waves, but at slower velocity because they travel in a shearing motion perpendicular to the direction of travel. It is because of this shearing that they are stopped entirely by the liquid core. This creates an even broader shadow zone everywhere beyond 104 degrees. It was this lack of S-wave arrivals and recognition of the slowing of the P-wave velocity that caught the attention of seismologists in 1910. By understanding how energy is refracted by different materials and pressures, it enabled them to deduce a liquid outer core. By 1913, the P-wave shadow zone between 104 and 140 degrees was refined to define the core mantle boundary. Remember, these show just two of the types of seismic waves that migrate away from an earthquake. Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake rupture and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and soil conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The light bulb represents the location within the Earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb,
The magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb at any spot in a room. A small light bulb in one area of a room will make that area bright with high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps. If you predict that an earthquake will happen on January 1st, you'll be right. Over 2,000 earthquakes are located by the USGS every day worldwide, so there's a 100% chance that there will be an earthquake on January 1st, but most of them are so small that they're not felt. 80% of the world's earthquakes occur around the Pacific Rim, but they could occur at any location. As an example, if you predict that an earthquake will happen between, say, San Bernardino and the Salton Sea this year, well, you'll be right. There were 12,800 measurable quakes in the past 12 months, and that pattern will likely continue next year. If you predict that there will be an earthquake greater than a strong magnitude 7 this year, you'll be right, because there are usually about 18 magnitude 7 and greater earthquakes every year. Even if you drop the magnitude to a felt magnitude 4 or larger quake in California in the next year, you could be right, because California has about 15 to 20 every year. The 12 months before July 3rd, 2019, had 19 quakes between magnitude 4 and magnitude 5. The Ridgecrest earthquake sequence has had 76 magnitude 4 or greater aftershocks. Thus, for a prediction to be meaningful, it has to specify a time, location, and magnitude range that is unlikely to occur randomly.
Este não está em cima de um aspirador?
Não, é uma caixa.
Pois eu sei, mas parece aqueles vídeos que se vêem dos gatinhos em cima daqueles aspiradores automáticos.
Sim, eles adoram.
Passear pela casa, fez.
Seismic hazard is the probability of ground shaking due to earthquakes and other effects of earthquakes, including ground rupture, landslides, tsunamis, and soil liquefaction. Seismic risk is the likelihood that humans might sustain injuries and fatalities, plus economic losses due to the hazard. Risk and the perception of risk are not always aligned. A seismic hazard map assesses the possibility of future ground shaking at a location based on the past history of nearby earthquakes and ground shaking, plus what we know about faults in the area from geologic, geodetic, and seismological information. The hazard also depends on how the ground responds to shaking, which depends on the subsurface rock layers. In an open field, someone experiencing strong shaking would just fall down. Hence, most seismic risk comes from the possible collapse of buildings due to shaking. Let's look at two examples. A person in a high seismic hazard zone in a well-engineered high-rise has low seismic risk. A weak structure built in a low seismic hazard zone may have high seismic risk from even light shaking. Risk assessment takes into account the hazards, population density, man-made structures, weak building materials, and more. Again, a seismic hazard is the probability that earthquake shaking of a certain intensity will occur in a given geographic area within a given window of time. From that, risks can be assessed and included in mitigation efforts.
In 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon, but what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave's speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this destructive force of nature? People in some areas have attempted to stop tsunamis with seawalls, floodgates, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.
Ainda estás a completar a apresentação?
Pois, ainda não pus tudo, mas pus o essencial.
Ok.
Tinha aqui um que abri há bocadinho. Deve ser interessante.
Este já vimos. Quer dizer, este era do tsunami, não era?
Este aqui, eu não sei se estou...
Apareceu esta imagem do cérebro quando foi o tsunami, mas se calhar...
É porque é tudo da mesma coleção.
Já vi. Já vi que ele tem tsunamis na cabeça e mais coisas.
Tem.
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers used models, like a two-dimensional array of lines representing columns and beams, or a single-line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible.
É japonês ou chinês? É japonês, não?
Acho que sim.
Bandeirinhas e manos, mas parece chinês com as bandeirinhas. Parece a China.
Example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the
Também há ressonância aqui.
back and forth movements
Olha ali o bicho mau.
which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far...
Quero viver num prédio daqueles, não cai nem por nada.
Today,
Já estava quase no chão e voltava para cima.
at building sites, in order to prevent resonance-induced collapses.
Era mesmo elástico, sem quebrar.
Soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
Smart one.
Achei muito engraçado.
É engraçado, tá?
Oi, agora é isto.
Vou ali buscar uma frutinha, já venho.
Sim.
In 132 CE, Chinese polymath Zhang Heng presented the Han court with his latest invention. This large vase, he claimed, could tell them whenever an earthquake occurred in their kingdom, including the direction they should send aid. The court was somewhat skeptical, especially when the device triggered on a seemingly quiet afternoon, But when messengers came for help days later, their doubts turned to gratitude. Today, we no longer rely on POTS to identify seismic events, but earthquakes still offer a unique challenge to those trying to track them. So why are earthquakes so hard to anticipate, and how could we get better at predicting them? To answer that, we need to understand some theories behind how earthquakes occur. Earth's crust is made from several vast, jagged slabs of rock called tectonic plates, each riding on a hot, partially molten layer of Earth's mantle. This causes the plates to spread very slowly, at anywhere from 1 to 20 centimeters per year. But these tiny movements are powerful enough to cause deep cracks in the interacting plates, and in unstable zones, the intensifying pressure may ultimately trigger an earthquake. It's hard enough to monitor these minuscule movements, but the factors that turn shifts into seismic events are far more varied. Different fault lines juxtapose different rocks, some of which are stronger or weaker under pressure. Diverse rocks also react differently to friction and high temperatures. Some partially melt and can release lubricating fluids made of superheated minerals that reduce fault line friction. But some are left dry, prone to dangerous buildups of pressure. And all these faults are subject to varying gravitational forces, as well as the currents of hot rocks moving throughout Earth's mantle. So which of these hidden variables should we be analyzing, and how do they fit into our growing prediction toolkit? Because some of these forces occur at largely constant rates, the behavior of the plates is somewhat cyclical. Today, many of our most reliable clues come from long-term forecasting related to when and where earthquakes have previously occurred. At the scale of millennia, this allows us to make predictions about when highly active faults, like the San Andreas, are overdue for a massive earthquake. But due to the many variables involved, this method can only predict very loose timeframes. To predict more imminent events, researchers have investigated the vibrations Earth elicits before a quake. Geologists have long used seismometers to track and map these tiny shifts in the Earth's crust. And today, most smartphones are also capable of recording primary seismic waves. With a network of phones around the globe, scientists could potentially crowdsource a rich, detailed warning system that alerts people to incoming quakes. Unfortunately, phones might not be able to provide the advance notice needed to enact safety protocols. But such detailed readings would still be useful for prediction tools like NASA's QuakeSim software, which can use a rigorous blend of geological data to identify regions at risk. However, recent studies indicate the most telling signs of a quake might be invisible to all these sensors. In 2011, just before an earthquake struck the east coast of Japan, nearby researchers recorded surprisingly high concentrations of the radioactive isotope pair, radon and thoron. As stress builds up in the crust right before an earthquake, microfractures allow these gases to escape to the surface. These scientists think that if we built a vast network of radon-thoron detectors in earthquake-prone areas, it could become a promising warning system, potentially predicting quakes a week in advance. Of course, none of these technologies would be as helpful as simply looking deep inside the Earth itself. With a deeper view, we might be able to track and predict large-scale geological changes in real time, possibly saving tens of thousands of lives a year. But for now, these technologies can help us prepare and respond quickly to areas in need, without waiting for directions from a base. Keep exploring the terrifying power of nature with this playlist.
Não estou aqui, mas estou a ver-te. Quer dizer, melhor, tu não me estás a ver, mas eu estou a ver-te.
Exato. Já vamos ver mais coisas.
Pois, está bem.
Major and great earthquakes are usually followed by hundreds or even thousands of smaller earthquakes called aftershocks that occur along and adjacent to the fault displaced during the large earthquake. In some earthquake sequences, a smaller earthquake called a foreshock precedes the main shock, like the one that occurred 2 days before the 2011 Tohoku-oki magnitude 9.1 earthquake. With rare exceptions, all magnitude 7 to magnitude 9 earthquakes have a collection of smaller magnitude aftershocks that can occur for weeks, years, or even centuries after the main shock. On the other hand, many major and great earthquakes do not have a foreshock preceding the main shock. Important observations about foreshocks and aftershocks are provided by the 2002 magnitude 7.9 earthquake in the Alaska Range. First, some background. The Alaska Range is a narrow, 650-kilometer-long mountain range far from the subduction zone plate boundary. The Yakutat terrain was an oceanic plateau that traveled northwest on the Pacific Plate and began colliding with the continental margin about 25 million years ago. It now acts like a geologic snowplow, driving immense blocks of continental crust in a counterclockwise rotation. Right lateral strike-slip faulting along the Castle Mountain and Denali faults accommodate this crustal block rotation. At a magnitude 7.9, the November 3rd, 2002 Denali main shock was one of the largest strike-slip earthquakes in North America. The earthquake rupture started at a depth of 5 kilometers, with 4 meters of displacement on the previously unknown Susitna Glacier fault. It continued with up to 8 meters of right lateral displacement on the Denali fault, and then branched onto the Tachunda fault for a total rupture length of 340 kilometers. Let's now examine the entire sequence of earthquakes that occurred along the Denali Fault from late 2002 into 2003. The sequence started on October 23rd with the magnitude 6.7 Nenana Mountain earthquake that was followed by aftershocks spread over a 45-kilometer-long segment of the Denali Fault. The resulting fault displacement decreased shear stress on that part of the fault, but increased stress on the adjacent segment to the east. On November 3rd, the magnitude 7.9 main shock occurred, with the epicenter located 22 kilometers east of the magnitude 6.7 epicenter. The October 23rd earthquake is now called a foreshock because it triggered the magnitude 7.9 main shock 11 days later. However, we didn't know it was a foreshock until November 3rd, when the larger main shock occurred. That magnitude 7.9 main shock was destined to eventually occur, but was hastened by the changing stress caused by the foreshock. Seismologists have analyzed countless foreshock main shock pairs of earthquakes and earthquake triggering in general. Unfortunately for earthquake prediction, there are no special characteristics of an earthquake that let us know it is a foreshock of a larger main shock that is yet to come. The major redistribution of stress during the main shock triggered an aftershock sequence of smaller earthquakes along the main shock rupture zone. Aftershocks are smaller earthquakes on patches of the rupture zone and adjacent smaller faults that occur as rocks along the rupture adjust to the new state of stress. 760 aftershocks of magnitude 3 or larger occurred during the 30 days following the November 3rd main shock. The entire earthquake sequence reduced a large amount of shear stress that had built on the Denali Fault over the preceding decades and centuries. 14 aftershocks had magnitudes greater than 5, and the largest occurred 10 minutes after the main shock, with a magnitude of 5.6. In general, larger aftershocks are concentrated in the hours to days following the main shock. Remember, the magnitude scale is logarithmic, and elastic energy released by an earthquake increases by a factor of 33 with every unit increase in magnitude. So, at a magnitude 5.6, the largest aftershock released less than 1/1000th of the energy released by the magnitude 7.9 main shock. On this graph, we can see that the rate of aftershock dies off with time after the main shock. This rapid decay in the rate of aftershocks was first studied in detail by Fusakichi Omori, one of the most important figures in the history of seismology. Omori examined aftershocks of the magnitude 8 Nobi earthquake that occurred in central Japan in 1891. The Nobi earthquake is the largest instrumentally recorded inland earthquake in Japanese history. Omori found that the decay of the aftershock rate was best analyzed using a logarithmic graph of aftershocks per day versus days after the main shock. He showed that the rate of Nobi aftershocks decreased with the reciprocal of time since the main shock. This is a general observation now referred to as Omori's law. Plotting data for the 2002 Denali earthquake sequence on a logarithmic graph shows that the decay in the aftershock rate follows Omori's law. In a typical main shock aftershock sequence, 97% of the energy is released by the main shock, while the hundreds to thousands of aftershocks release the remaining 3%. Although only a portion of the energy of an earthquake sequence is released by the aftershocks, the largest aftershocks and the highest rate of aftershocks occur during the critical first hours and days immediately following the major earthquake. This is exactly the time when emergency workers are locating and rescuing injured people from collapsed or damaged buildings. Because those buildings can shift or even collapse during aftershocks, rescuers are at greatest risk when their expertise and service is most important.
you live in earthquake-prone regions, it isn't a question of if, but when an earthquake will occur. We do not know where we will be when it strikes, but we can know how to protect ourselves when it happens. Here are the best ways to protect yourself when an earthquake strikes. If you are inside a building, do not run outside. Drop, cover, and hold on. Drop to your hands and knees. Take cover under something sturdy and cover your head and neck, and hold on until the shaking stops. If you are in bed, roll onto your stomach. Cover your head and neck with a pillow and hold on. If you are in a classroom, take cover under a desk and hold on. If you are in a lab or other area with chemicals or machinery, be aware of all hazards before you drop, cover, and hold on. If you are using a wheelchair or walker, lock your wheels if possible, then cover your head and neck and hold on until shaking stops. If you are in a high rise, drop, cover, and hold on. When shaking stops, use the stairs. Do not use the elevator. In a store or where there are freestanding shelves, move quickly to a protected area next to a shopping cart or beneath clothing racks. Then drop, cover, and hold on. If you are outdoors, move quickly away from buildings to avoid falling debris or away from power lines and other hazards. Drop, cover, and hold on. If driving, pull over, avoiding overpasses, bridges, power lines, and other hazards. Stop, set the parking brake. Stay in the vehicle until shaking stops. If you are near a shoreline, a tsunami may be coming. Drop, cover, and hold on, then stand and move quickly to high ground or inland. Stay there until tsunami restrictions are lifted. What you do during an earthquake depends on where you are, but the basics will remain the same. It can be difficult to run or even walk when the ground is shaking. Drop and crawl if you need to move to a safer location. The greatest danger during an earthquake is from falling or flying objects, which is why you need to take cover. Protect your head and neck with your arms or with other objects. Earthquake shaking can last from seconds to several minutes. Hold on for the entire time. For more information on earthquake protective actions and how to get prepared, visit www.shakeout.org.
Estás a explorar os links ou já os conheces?
Alguns já.
Mas este é de Puerto Rico. Tectonics and Earthquakes of Puerto Rico. O Luís Matias está a perguntar como é que podes partilhar, mas tu ainda não tens os links tens os links dentro da apresentação?
Não, porque eu descarreguei os vídeos, mas posso fazer uma lista. Mas são todos que estão na apresentação, são todos da Iris.
Sim. Depois podes pôr no Google Drive ou assim, se quem quiser.
A travel time curve is a time versus distance graph of the time that it takes for seismic waves to travel from the hypocenter of an earthquake or other ground shaking event to seismograph stations varying distances away. They're constructed by analyzing thousands of earthquakes from hundreds of seismograph stations around the world, and they're used by seismologists to quickly locate earthquakes. But how were they determined?
To explain, we'll use a simple graph of P, S, and surface wave arrival times while exaggerating the relative motion as the waves hit the buildings, representing seismic stations. Here, we show an earthquake near the top of the globe and graph the seismic wave arrival times to recording stations at increasing distances from the hypocenter, which is the location below the surface where the earthquake actually occurred. The y-axis shows distance from the earthquake, and the x-axis shows the elapsed time since the event. The seismograms record the arrivals of the compressional P, the shearing S, and the rolling surface waves. These motions are also reflected in the motions of the buildings. Seismic waves travel at different rates, so the farther a seismic station is from an earthquake, the farther apart the P, S, and surface wave arrival times will be. Here, we show only direct P and S wave paths through the mantle and crust. The final image of this animation will show more of the complexity within the Earth as the waves are reflected, refracted, and damped due to changes at depth. Connecting the waves through the stack of seismograms creates the travel time curves that can be used to locate earthquakes. Simply stated, the time difference between the arrival of the P wave and the arrival of the S wave can be used to measure the distance from the seismometer to the epicenter. This iris poster of the 1994 Northridge, California earthquake reveals more of the complexity beyond just P, S, and surface waves. That earthquake killed 51 people, caused over $20 billion in damage, and raised the Santa Susana Mountains north of Los Angeles by 70 centimeters, or 28 inches. It also created seismic waves that ricocheted throughout the Earth's interior and were recorded at geophysical observatories around the world. The paths of some of those seismic waves and the ground motion that they caused are shown on the globe. Subduction zone megathrust earthquakes, the most powerful earthquakes, can produce tsunamis through a variety of structures that are missed by simple models. The basic model shows rock above the convergent plate boundary being compressed and bent as it stores elastic energy. Once friction is overcome, the overriding plate slides abruptly up the fall, causing the leading edge to heave seawater upward, generating a tsunami. This shallow angle reverse fall is called a thrust fall because the overlying plate thrusts up over the subducting plate. Let's explore different tsunami-producing mechanisms by examining three famous earthquakes. In 2011, the magnitude 9 Japan earthquake ruptured a fault area 500 kilometers long by 200 kilometers wide over an interval of nearly 3 minutes. Surveys of seafloor bathymetry before and after the earthquake document up to 50 meters of fault displacement at the Japan Trench. What would that look like in cross-section? During the rupture process, the overriding plate slid up the west-dipping fault plane. That uplifted the seafloor by 10 meters, producing the local tsunami that rushed on shore within 20 minutes of the earthquake, and the distant tsunami that spread over the Pacific Ocean basin. Due to effective emergency education, 96% of the citizens evacuated the tsunami inundation zone to survive this natural disaster. Next, let's examine how deformation, as well as fault displacement of the overriding plate can produce a tsunami. The 2010 magnitude 8.8 Chile earthquake tore a rupture zone 600 kilometers long by 130 kilometers wide. Although the rupture began at approximately the same distance from the trench,
there was little to no displacement at the trench as there was during the Japan earthquake. So, what generated the local tsunami that resulted in 123 deaths and produced major damage in coastal towns? Fault displacement ranged from 5 meters at the hypocenter beneath the coast to 10 meters midway to the trench, then decreased to little or no displacement at the trench. Westward displacement of the continental shelf above the plate boundary caused broad uplift of the seafloor. In addition, the change in amount of displacement along the plate boundary caused internal deformation of the overriding plate. These effects combined to uplift the ocean floor by 2 to 3 meters. This sudden uplift generated the deadly local tsunami along the coast of South America and Juan Fernandez Islands. Alerted by strong ground shaking, coastal residents evacuated to high ground. Unaware of the danger, many vacationers did not evacuate and became victims of the tsunami. Our third example introduces splay faulting during the rupture. The 1964 magnitude 9.2 Great Alaska earthquake ruptured a major segment of the eastern Aleutian subduction zone, 800 kilometers long, lasting over 4 minutes. The continental shelf and slope of the overriding North American plate was uplifted over 9 meters, while inboard areas subsided as much as 2 meters. This sudden displacement of the ocean floor generated the tsunami that claimed lives from Alaska to Northern California. Less than 2 meters of regional uplift occurred at the trench. So what caused the 9-meter uplift of the continental shelf and generated the tsunami? In this example, we will show that there were 3 contributing factors to the devastation that ensued. With few seismometers in the region in 1964, the progression of the rupture relative to the splay faults is unknown. For simplicity, we'll show plate boundary displacement branching into splay faults. During this earthquake, displacement started on the plate boundary megathrust fault, producing 2 to 4 meters of regional seafloor uplift and subsidence. However, most of the fault offset ramped up to the seafloor on splay faults like the Patton Bay fault that was displaced 9 meters. Because displacement on steeply dipping splay faults causes larger uplift of the ocean floor, a bigger tsunami is produced, and it starts closer to shore, providing less time to evacuate. In steep-sided fjords and inlets, ground shaking caused landslides, some entirely below sea level, resulting in surges of seawater up to 50 meters high that struck coastal towns, including Seward and Valdez. This third type of tsunami took 77 lives. In these vulnerable locations, the usual drop, cover, and hold on response to ground shaking must become evacuate immediately from low ground, even during earthquake ground shaking. The tsunami-producing mechanisms illustrated here are still just a glimpse into the variety of subduction zone earthquake faulting and folding processes. The Alaska 1964, Chile 2010, and Japan 2011, as well as the catastrophic 2004 Sumatra subduction zone megathrust earthquakes, have delivered powerful lessons that rapid evacuation of tsunami inundation zones is a life-saving emergency response.
Estou cansada. É muita exigência intelectual para ver estes vídeos todos.
Earthquakes are caused by the movement of the huge tectonic plates that continents sit on. What happens is they come together. One, in this case, the Pacific plate, is moving below the Japanese or Eurasian plate. And it causes that plate to bend when it sticks there. Now, it will stick, pressure builds up until suddenly it's flipped. Have a look at this. Now, this is the tectonic plate that Japan is sat on. And here's the Pacific plate coming down underneath it. Now, normally they want to move together at about 9 centimeters a year. But sometimes they get stuck. And when they get stuck, energy of the moving together gets translated to strain energy, literally flex and bend huge slabs of rock. And that energy builds and builds, flexing and bending more and more. When they finally slip, that stored energy, all that twist and bend in the rock gets released in a sudden movement. Like that. As you can see, it literally flicks up, moving the ocean floor above it, which moves the ocean, causing a tsunami. So here we've got a bigger submarine version of what's going on. This gives a representation of what's been happening 24 kilometers below the ocean surface and trends. And these things work in what we call a six-sit way. Most of the time they're stuck, but occasionally they sit. And that's what an earthquake is. So we've got it here, this vent up here, full of pent-up energy, waiting to slip. And when the slip happens, that energy gets released into the ocean, causing a series of tsunami waves, moving in both directions across the earthquakes.
Data gathered during the 2011 Tohoku earthquake taught us much about megathrust earthquakes. The largest magnitude earthquakes that affect both Japan and the Pacific Northwest occur along the shallow portions of the offshore subduction zone plate boundaries. With over 4,000 modern seismograph stations deployed across the country, Japan implemented an earthquake early warning plan to issue alerts about impending ground shaking and tsunamis. Earth-deriving P waves locate the epicenter and estimate the magnitude, then trigger an alert to nearby population centers via sirens, automated phone messages, TV, and radio before the slower, damaging S waves arrive. This works well for strong magnitude 6 and major magnitude 7 earthquakes. But the March 2011 magnitude 9 Tohoku earthquake revealed limitations of the seismic early warning system and taught us how GPS can improve warnings for great earthquakes of magnitude 8 or 9. During that earthquake, P waves from the initial rupture located the epicenter and estimated a magnitude. Early warnings indicated that shaking produced by slower but larger S waves would hit Sendai in just 8 seconds and Tokyo in 80 seconds. These arrival times were accurate, but the intensity and duration of ground shaking were greater than expected because the system vastly underestimated the magnitude. Here's why. In its simplest form, an early warning system assumes the earthquake results from sudden slip on a small area of a fault surface. But for earthquakes greater than magnitude 7, the small patch at the epicenter is just the starting point for a rupture that spreads over a huge area as it tears the fault and radiates immense seismic energy from all parts of the rupturing fault area. The magnitude 9 Tohoku earthquake ripped a fault area 300 miles long, releasing seismic energy over an interval of nearly 3 minutes. Let's show how GPS can enhance earthquake early warning by using a simplified cross-section of the Tohoku earthquake. As S waves traveled past the nearest GPS stations, the ground moved more than 14 feet toward the epicenter in 45 seconds. At the same time, near the Japan Trench, the ocean floor uplifted 23 feet, generating a tragic tsunami that rushed on shore minutes after ground shaking ended. At 95 seconds, GPS revealed large ground motions that indicated a great subduction zone earthquake was rupturing offshore and a tsunami was certain to follow. This data could have given coastal communities a far more urgent tsunami alert and Tokyo an additional minute to prepare for the shaking that would be much stronger than initially calculated. Can an earthquake early warning system be developed for Cascadia subduction zone earthquakes? Indeed, it can. With a coordinated effort by seismologists and geodesists, a better earthquake and tsunami early warning system is possible. To understand the components of early earthquake warnings, let's watch an animation of a hypothetical magnitude 9 Cascadia subduction zone earthquake. The epicenter is offshore of Port Orford, a scenario to give optimal warning times for Portland and Seattle. The earthquake generates seismic waves as it ruptures north of the zone. 10 seconds after the P waves hit the coast, the seismic network locates the hypocenter and determines the magnitude as 7 or larger. It cannot say how much larger. As S waves arrive, the Port Orford GPS station lurches seaward, indicating significant ground displacement. Knowing they might have little time after shaking stops to reach high ground, residents evacuate immediately. 20 seconds after initiation, rupture moves past Cape Blanco. S waves produce strong ground movement, and the Cape Blanco GPS station lurches 10 meters, indicating that the Port Orford station wasn't a fluke data point, but that this earthquake is greater than magnitude 8.5. Tsunami warnings are issued for coastal communities and broadcast throughout the Pacific Ocean. Coastal towns farther north, like Coos Bay, Oregon, have about 20 seconds warning, which allows people to drop, cover, and hold on, get away from dangerous machines or chemicals, and shut down gas and electric supply lines. Region-wide emergency signals are issued indicating when strong ground shaking will arrive. Portland is warned that damaging S waves will arrive in 80 seconds. Seattle has a 2-minute and 20-second warning. 1 minute after the earthquake rupture began, P waves arrive in Portland. As the rupture and S waves reach New Portland, we will see that GPS station lurch southwest, indicating the earthquake will approach magnitude 9. Strong shaking affects the inland valleys east of the ongoing rupture as it generates more seismic waves. 2 minutes after initiation, Seattle feels the initial P waves jolt. The S waves, generated by the rupture offshore west of Portland, begin producing the most violent ground shaking in Portland. Shaking lasting up to 5 minutes will damage older, unreinforced buildings. This animation shows that Portland and Seattle could have several minutes warning before the strongest shaking hits. With a minute of warning, additional precautions include stopping rail and road traffic, closing bridges and tunnels, halting airport takeoffs and landings, opening elevator doors at the nearest floor, stopping surgeries, and getting emergency personnel and equipment ready to respond. At 3 minutes, S-waves arrive in Seattle as the rupture passes north of Astoria, where GPS stations move southwest by 5 meters, confirming a magnitude of 9. Rupture has progressed north to offshore Vancouver Island, with violent ground shaking continuing in Seattle for several more minutes. We know that a rupture like this one depicted here, along the entire length of the Cascadia subduction zone, last occurred on January 26, 1700. A similar scenario could occur with an epicenter initiating anywhere along the subduction zone boundary. In addition to a joint seismic and GPS network, an early warning system requires public education, as well as an integrated plan with civil protection authorities and telecommunications groups to make such a system effective for saving lives.
Ascertain the exact epicenter. They've been in contact with the National
In this video, you'll learn how to protect yourself and how to behave properly during an earthquake. An earthquake is one or multiple series of vibrations on the ground that can cause serious damage to persons and property. During an earthquake, do not run away. Falling objects represent a danger. If you're inside, take shelter under a sturdy piece of furniture or in the corner of a wall. Stay away from windows and mirrors. Do not face them. Cover your head and neck. If you're outside, stay away from buildings and everything that could collapse. If you're driving, pull up your car at a safe distance from everything that could fall down. Stay inside your car until the earthquake is over. After the earthquake, be careful, there might be aftershocks. Listen to the radio for safety instructions. Close the water and gas inlet taps. Open windows and doors in the event of a gas leak. Leave the building. Don't use an elevator. Make your way to an open space. Eventually, head for a meeting point. Take your personal documents, warm clothes, and essential medication with you. Walk in the middle of the road and pay attention to falling objects. Don't smoke and don't light candles because of an explosion risk. Don't touch falling power lines. Don't make phone calls in order not to congest the telephone network. School children are taken care of at school. It is dangerous and not necessary to pick them up. Block access to damaged buildings. Stay away from coastal areas as there may be a risk of a tsunami. Make sure that your neighbors, especially if they're old or handicapped, do not need help. How to address the risk. Familiarize yourself with possible natural catastrophes in your country and safeguard measures. Arrange a meeting point for your family. Prioritize earthquake-resistant house constructions. Select your shelter areas. Store dangerous items properly in order to prevent them from falling. Secure devices and heavy pieces of furniture. Prepare your emergency disaster kit and first aid kit.
Professor, está a ouvir-me?
Pronto. Liliana, já estou disponível. Diz lá.
Na apresentação, para pôr
Peraí,
aqui...
deixa-me pôr isto, sou mais alto. Sim. Aquilo está a correr, mas não consigo parar aquilo, pá.
Está porque estava na forma automática, ou seja, quando clica em apresentar, aqui tem 3 formas.
Estou. Ficaste paralisado.
Although more closely hitched to the seasons than the Julian, the Gregorian calendar still isn't perfect.
Liliana, diz lá.
Estava a dizer que quando é na apresentação tem que ser apresentar e tem que ser no tipo padrão. Aí é que se vai passando como é no PowerPoint.
Espera aí, deixa-me abrir então. Ele abriu. Pá, mas ele começa logo a mexer.
Ok.
Eu carreguei no link e ele começa logo a mexer.
Mas
eu não fiz apresentação nenhuma.
Mas eu pus a opção como pode editar. Bom, mas eu vou pôr o e vou...
Sei lá, porque aí perguntou se eu queria editar. Pronto, e ele pediu-me um login e não sei quê, não sei quantos.
Sim.
Mas depois, assim que eu entrei, começou logo a mexer.
Não sei se com este ele já vai deixar ser faseado, porque estava na opção automática.
Então, espera aí, onde é que tu estás? Ok, então deixa-me clicar aqui. Pronto, ele está a mexer, mas será que posso fazer alguma coisa para ele parar?
Ele está a mexer, mas ainda não mudou de slide, pois não?
Não, não.
Então se o professor carregar como se estivesse a trabalhar no PowerPoint, no seguinte, e depois para o outro se o vídeo mexe. No terceiro slide há cá um vídeo.
Pronto, ok, ele está a mexer também. O que é um sismo com um vídeo, sim. Portanto,
Pronto.
a ideia é passar manualmente, é isso?
Sim, neste caso sim.
Porque ele, cada vídeo, vai voltar ao princípio, não é?
Não, ele passa o slide e passa o vídeo ao mesmo tempo que está a passar o slide e acaba.
Sim, mas
o vídeo.
quando terminar? Quando
terminar ele fica no último slide, a pessoa pode voltar ao início, sim.
Não, estou a dizer, quando terminar este slide, ele passa imediatamente para o seguinte ou precisa que
Não, tem que ser clicado, sim.
Tem que ser clicado?
Sim.
Está bem. Ok. Pronto, olha, vou deixar isto a correr. Obrigado pela... Depois nós combinamos como é que isto pode ser depois partilhado lá na nossa área. Ok, já estou a ouvir. Ok, Liliana, obrigadão.
Nada.
Concept coined by Robert Knott to help people visualize an earthquake's location. The epicenter is the map location on Earth's surface above where the earthquake began. An earthquake actually begins inside the Earth at the hypocenter.
Estás a ver?
The hypocenter ranges from several to hundreds of kilometers below the epicenter in Earth's outer brittle layers. What do we mean by the earthquake begins? Let's place a grid on the strike-slip fault surface. A small earthquake releases energy at its hypocenter suddenly, like a blast of TNT. But an earthquake is not like a bomb. The area where the rock ruptured or broke is small, and the distance the rocks moved is small. A magnitude 4 typically ruptures about 1 square kilometer. A magnitude 6 ruptures about 100 square kilometers. Often, there is no surface faulting at the epicenter, but if an earthquake is shallow and the rupture area grows vertically, it can offset the ground surface or create a fault scarp. All earthquakes, including the largest earthquakes like this one on the subduction zone fault, began at the hypocenter. Seismic and heat energy are continuously released as the rupture spreads, as though it were unzipping the rough surface of the fault, sticking and slipping during the chain reaction. The earthquake stops when the fault stops slipping. Computers can make
ascertain the exact epicenter. They've been in contact with the National Earthquake Center.
News reports commonly refer to an earthquake's epicenter. The word is a concept coined by Robert Mallet to help people visualize an earthquake's location. The epicenter is the map location on Earth's surface, above where the earthquake began. An earthquake actually begins inside the Earth at the hypocenter. The hypocenter ranges from several to hundreds of kilometers below the epicenter, in Earth's outer brittle layers. What do we mean by the earthquake begins? Let's place a grid on the strike-slip fault surface. A small earthquake releases energy at its hypocenter, suddenly, like a blast of TNT. But an earthquake is not like a bomb. The area where the rock ruptured or broke is small, and the distance the rocks moved is small. A magnitude 4 typically ruptures about 1 square kilometer. A magnitude 6 ruptures about 100 square kilometers. Often, there is no surface faulting at the epicenter, but if an earthquake is shallow and the rupture area grows vertically, it may offset the ground surface or create a fault scarp. All earthquakes, including the largest earthquakes like this one on a subduction zone fault, begin at the hypocenter. Seismic and heat energy are continuously released as the rupture spreads, as though it were unzipping the rough surface of the fault, sticking, slipping during the chain reaction. The earthquake stops when the fault stops slipping. Computers can If the Earth had no changes with depth, seismic waves would travel straight paths. But the Earth has composition, density, and temperature changes that cause the seismic waves to refract as velocity in the mantle generally increases with depth. We can zoom into a shallow part of the crust to watch how waves behave when crossing into boundaries of higher velocity. We will track two paths from the earthquake. The direct path travels to station X through the slowest layer. The outer path continually refracts as it crosses boundaries of increased velocity until the incident ray reaches a critical angle and begins sending a head wave to the surface. These head waves return to the surface, refracting back at the same angles and velocities that they descended with. This is because they follow Snell's law at each boundary, with relative velocities now decreasing upward. Some of the critically refracted waves reach station X and beyond before the blue direct wave which took the shortcut. This is because the velocity increases were great enough to overcome the slower direct path. The dashed black line emphasizes how much the wave is refracted in each layer.
Let's see.
concept of a seismic shadow zone as a global effect of an earthquake is an oversimplification that ignores a broad array of refracted, reflected, and diffracted seismic waves that propagate through the Earth. For now, we'll just focus on direct, compressional P and shearing S waves. These are body waves that take the most direct routes within the Earth and do create shadow zones, which are useful for teaching Earth structure. An earthquake, depicted here at the top of the globe for convenience, sends compressional P waves in all directions, refracting along boundaries with depth, causing curved paths. At the core mantle boundary, they are refracted or bent inward and slow down in the liquid. It's this refraction that causes a shadow zone between the angular distances from 104 to 140 degrees from the earthquake. S waves travel along the same path as the P waves, but at slower velocity because they travel in a shearing motion perpendicular to the direction of travel. It is because of this shearing that they are stopped entirely by the liquid core. This creates an even broader shadow zone everywhere beyond 104 degrees. It was this lack of S-wave arrivals and recognition of the slowing of the P-wave velocity that caught the attention of seismologists in 1910. By understanding how energy is refracted by different materials and pressures, it enabled them to deduce a liquid outer core. By 1913, the P-wave shadow zone between 104 and 140 degrees was refined to define the core mantle boundary. Remember, these show just two of the types of seismic waves that migrate away from an earthquake. Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake rupture and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and soil conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The bulb represents the location within the earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light bulb that a small light bulb in one area of a room will make that area bright, high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps. If you predict that an earthquake will happen on January 1st, you'll be right. Over 2,000 earthquakes are located by the USGS every day worldwide, so there's a 100% chance that there will be an earthquake on January 1st. But most of them are so small that they're not felt. 80% of the world's earthquakes occur around the Pacific Rim, but they can occur at any location. As an example, if you predict that an earthquake will happen between, say, San Bernardino and the Salton Sea this year, well, you'll be right. There were 12,800 measurable quakes in the past 12 months, and that pattern will likely continue next year. If you predict that there will be an earthquake greater than a strong magnitude 7 this year, you'll be right, because there are usually about 18 magnitude 7 and greater earthquakes every year. Even if you drop the magnitude to a felt magnitude 4 or larger quake in California in the next year, you could be right, because California has about 15 to 20 every year. The 12 months before July 3rd, 2019, had 19 quakes between magnitude 4 and magnitude 5. The Ridgecrest earthquake sequence has had 76 magnitude 4 or greater aftershocks. Thus, for a prediction to be meaningful, it has to specify a time, location, and magnitude range that is unlikely to occur randomly. Seismic hazard is the probability of ground shaking due to earthquakes and other effects of earthquakes, including ground rupture, landslides, tsunamis, and soil liquefaction. Seismic risk is the likelihood that humans might sustain injuries and fatalities. Economic hazard. Risk and the perception of risk are not always aligned. A seismic hazard map assesses the possibility of future ground shaking at a location based on the past history of nearby earthquakes and ground shaking, plus what we know about faults in the area from geologic, geodetic, and seismological information. The hazard also depends on how the ground responds to shaking, which depends on the subsurface rock layers. In an open field, someone experiencing strong shaking would just fall down. Hence, most seismic risk comes from the possible collapse of buildings due to shaking. Let's look at two examples. A person in a high seismic hazard zone in a well-engineered high-rise has low seismic risk. A weak structure built in a low seismic hazard zone may have high seismic risk from even light shaking. Risk assessment takes into account hazards, population density, man-made structures, weak building materials, and more. Again, a seismic hazard is the probability that earthquake shaking of a certain intensity will occur in a given geographic area within a given window of time. From that, risks can be assessed and included in mitigation efforts.
In 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon, but what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this destructive force of nature? People in some areas have attempted to stop tsunamis through seawalls, riots, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.
Welcome to Tsunami Teacher USA's Tsunami Basics. This short video is intended to provide you with a basic understanding of tsunamis and how to protect yourself.
On the morning of December 29th at around 6 o'clock in the morning, they felt an earthquake occurred. Knowing from previous training that I had received as a mayor, he waited up a higher area.
In the next several minutes, you will learn what a tsunami is, how to recognize dangerous tsunami waves are coming, and what to do if you are in a tsunami hazard or evacuation zone. Tsunamis are a series of traveling waves often generated by earthquakes. In the deep ocean, the waves can be up to hundreds of miles long, yet only a few inches or a foot in height. So, if you are on a boat in the deep ocean, you might not notice a tsunami wave passing beneath you. As they approach the shallow coast, the wave heights will increase, and in extreme cases can be up to 100 feet high when they crash on shore. Tsunami waves travel very fast in the deep ocean, somewhere between 400 and 500 miles per hour, which is the speed of a commercial jet airplane. In this animation of the September 2009 Samoa earthquake and tsunami, waves took only 10 to 15 minutes to reach the coast of American Samoa, Samoa and Tonga, and later reached California in about 10 hours.
I wasn't in Florida before they got. We didn't even know it's going to, the earthquake is so strong that the tsunamis may fall. And it's going to occur just like the blinking of an eye. So please keep a higher ground.
The wave's energy can focus flooding inland along a road or up a river. Large debris such as cars and trees act as battering rams, causing destruction as the wave moves inland or recedes. The series of waves can continue to arrive every 5 to 60 minutes for several hours. The next wave can arrive before the previous one recedes, resulting in greater water heights and further flooding inland. The first wave also may not be the largest. These images give you an idea of what tsunami waves may look like to a person on the shoreline. The waves arrive as walls of water, not as typical breaking or curling wind or surf waves. At the coast, a tsunami wave will slow down, but the waves are still dangerous. This footage of the 2009 Samoa tsunami shows the ease with which a tsunami wave less than 1 to 2 feet high could carve. Remember, even small tsunamis can be extremely dangerous to swimmers and boats in harbors due to the strong wave current. If you see the ocean withdraw out to sea, exposing the ocean bottom, or hear the train-like roar of the tsunami, you might have less than a minute to get to safety. When an earthquake occurs near the coast, there may be only minutes before tsunami waves arrive. In this case, the natural warning signs are your alert to act immediately. Strong coastal earthquakes that shake for more than 30 seconds serve as a natural warning. Protect yourself first. Drop, cover, and hold on until the shaking stops. When it is safe, survey the area around you and evacuate by quickly walking inland and to higher ground. If wave arrival is imminent, consider vertical evacuation to the highest floors of a multi-story reinforced concrete building.
Hello, my lord. I looked out at the ocean and I saw the ocean was deep. It was going out. I could see the bottom of the ocean. I knew then that the tsunami was coming.
These images show the first tsunami wave after it receded at Pongo Plaza. The next wave inundating Pongo Plaza arrived within 10 minutes of the preceding wave.
Yeah, I could hear the wave was coming. I felt it.
This is a video of a small tsunami generated by an iceberg breaking apart. You will notice small waves are generated, followed by a loud roar produced by the waves. The tsunami then lifts up fishing boats and relentlessly smashes them onto the shore. All coastlines are vulnerable to tsunamis. Make sure you know your community's tsunami hazard and evacuation zone. Walk your tsunami evacuation routes so you know where they are located. Remember, in a local event, the natural warning signs are your earliest and possibly only alert. The U.S.'s West Coast Alaska Tsunami Warning Center and Pacific Tsunami Warning Center are monitoring earthquakes all the time and will issue official warnings, but they may not be in time to warn for a local tsunami. So do not wait for the official warnings. Given the tsunami's natural warning signs, act immediately.
Immediately we know it's going to, the earthquake is so strong, the tsunami may fall. And it's going to occur just like the breaking of an eye. So please, keep a higher ground.
Alô? Isabel?
Sim?
Olá, estou a ouvir, estou a ouvir.
Sim.
Não sei se me está a ver também, mas...
Eu consigo vê-lo. Eu queria
Ok.
mostrar esta sessão aos meus filhos.
Qual?
Tudo o que gostaria de saber sobre sismos e tsunamis. E sempre teve medo de perguntar. Eles são
Sim,
crianças.
sim, diga. Então é fazer perguntas sem medo.
É sem medo? Então, só um minuto.
Sim.
O meu filho mais pequeno tem 8 anos, vai fazer a pergunta.
Está bem.
Como é que acontecem os terremotos e os tsunamis?
Está bem. Olha, então, deixa cá ver. Eu vou encontrar aqui um boneco para te ajudar a explicar, está bem? Temos aqui preparado, deixa cá ver, pela Liliana. Ora bem, temos aqui o que é um sismo.
News reports commonly refer to an earthquake's epicenter. The word is a concept coined
Então,
by Robert.
vamos ver aqui, um sismo. Aqui não é a vibração do sismo. São as ondas sísmicas. Como se pagam as ondas sísmicas. Ok. Ora bem, mas... olha, estás-me a ver a mim? Estás-me a ver? Deixa-me parar aqui o... Ups, deixa-me parar aqui. Como é que te chamas?
Augusto. Agora tive
Como é que te chamas?
Augusto e esta é a Laura.
Augusto. Ok. Então vá. Estás-me a ver bem? Eu agora não sei se me estás a ver, se não. Estás-me a ver?
Não, só um minuto. Não.
Consegues-me ver?
Sim, consigo ver um painel.
Estamos a ver um ecrã branco.
Não, mas e a mim? Estás-me a ver a mim ou não?
Não conseguimos vê-lo, não.
Não me estás a ver a mim? Olha. Então, mas era suposto estás-me a ver, ora bem. Então, que a princípio o vídeo está ligado, deixa cá ver, só uma maneira de...
Sim, já ouvimos.
Já me estão a ver?
Sim.
Então, o que é que eu tenho na mão?
Na mão, como assim?
O que é que eu estou a segurar na mão? Ou nas mãos?
Uma folha.
Exatamente. Olha, então depois tu também podes mostrar aos teus colegas, amigos, que também sabes gerar um sismo. Então eu vou gerar um sismo aqui à tua frente, está bem? Para te explicar como é que se geram os sismos, ok?
Quero dizer uma coisa. Como a
Estás a
tua...
ver?
Sim, como a tela está com aquela coisa atrás de ti, eu não consigo ver muito bem o papel.
Não consegues ver bem o papel?
Sim, até parece a cara.
Está bem, mas estás a ver o papel?
Mais ou menos.
Pronto. Então vá. Eu vou gerar um sismo, está bem? Então está com atenção. Ouviste as ondas sísmicas?
Sim.
Então, imagina que esta folha de papel era a rocha que está por baixo dos nossos pés. Então, quando ela se rompe bruscamente, gera as ondas sísmicas como é o som que tu acabaste de ouvir, está bem? Isto é como se fosse um sismo, que é a ruptura brusca da rocha, está bem? Que liberta as ondas sísmicas, está bem? Portanto, o sismo, a vibração, é a propagação dessas ondas que são geradas quando a rocha se parte. Da próxima vez fazes tu, está bem?
Tá.
Geras tu o sismo, está bem? Já aprendeste a gerar um sismo?
Sim.
É isto que eu digo aos meus alunos também, que é para eles aprenderem como é que se gera um sismo.
Porquê é que a rocha se parte?
Isso agora, boa pergunta. Então, porquê é que a rocha se parte? Eu aqui tive que fazer força, não é? Tive que fazer força para rasgar a folha. E na Terra também existem forças que estão a atuar. Já ouviste falar nas placas tectónicas?
Sim.
A superfície da Terra parece que está parada, não é? Parece que está parada, mas de facto ela está-se a mover muito lentamente. E então esse movimento muito lento faz acumular forças na rocha. E quando a rocha deixa de aguentar essas forças, parte. Portanto, a nossa Terra, já viste como é que a nossa Terra também tem montanhas? Como é que achas que as montanhas são geradas? São geradas por essas forças muito lentas, que geram cadeias de montanhas e também são capazes de partir a rocha. São essas forças que nós chamamos de forças tectónicas. Portanto, é preciso forças e essas forças é a dinâmica do nosso planeta. Está bem?
Sim. E porquê que há tsunamis maiores que outros?
Essa do tsunami é mais fácil. Essa eu acho que tem um filme. Essa do tsunami é mais fácil para mostrar um filme, está bem? Ora bem, então vais poder ver este filme aqui, que eu estava a mostrar há bocadinho.
Welcome to Tsunami Teacher USA's Tsunami Basics.
Estás a ver o filme? Consegues ver o filme? Estás a ouvir o filme?
Sim.
Então, este senhor estava numa ilha, que é Samoa, e que sofreu um tsunami em 2009, um grande tsunami. Mas ele sobreviveu, porque sabe o que é que há de fazer quando ocorre um tsunami, está bem? Chega a ver aqui, baixar aqui.
How to recognize dangerous tsunami waves
Onde é que está
are
o som
coming,
disto?
and what to do if you are in a tsunami hazard or evacuation zone. Tsunamis are a series of traveling waves often generated by
Portanto, os tsunamis são uma série de ondas, não é uma onda. Atenção. Olha, vê agora como é que é gerado um tsunami. Portanto, é um tremor de terra no fundo do oceano que gera uma grande onda à superfície, ou ondas à superfície, que depois se propagam ao longo do oceano. Está bem?
The wave heights will increase, and in extreme cases, be up to 100 feet high when they crash on shore.
Podem ter atingido 30 metros de altura. Deixa eu ver aqui mais um.
And later be along a road or up a river.
Portanto, o tsunami é muito perigoso. Está bem? O tsunami é muito perigoso. Deixa eu ver aqui mais uma.
Tsunami wave will suggest 2,000. If you see the earthquake occurs near the coast, now
Também deves perceber que, olha, isto é extremamente importante, que é os tsunamis que afetam Portugal, Portugal continental, ocorrem muito próximo da costa. E por isso nós sentimos primeiro o sismo. E já deves ter feito o exercício na escola, não é? Já fizeste algum exercício? O que é que a gente deve fazer quando vem um sismo? Quando vem um sismo, devemos abrigar para não cair nada em cima da cabeça, agarrar e esperar. E então, isto é um sinal que pode vir um tsunami se nós estivéssemos próximo da costa. E então o que é que a gente deve fazer? Devemos subir para um lugar alto, está bem? Subir para um lugar alto.
Se estiveres em casa, estás bem. Okay.
Alô? Estás a ouvir?
Sim.
Pronto, agradeço.
Mas repara, o tsunami raramente atinge mais de 30 metros. Isso é um grande tsunami. Tu sabes qual é a altura da onda de Nazaré?
23 metros.
Mais.
46 metros.
A onda Nazaré é muito maior do que um tsunami. Mas é um problema. É que a onda Nazaré só tem pouca energia porque é causada pelo vento. Enquanto que o tsunami tem muita energia. Ele entra dentro de terra, continua, não para. Uma onda de vento vai e vem. E a onda do tsunami vem, está ali 2, 3, 4, 5 minutos, vai. Tem muita energia. Está bem? Portanto, há as ondas do vento e as ondas do tsunami. Não é pela altura que elas se distinguem, está bem? É pela energia, pela força que têm.
Ok.
Dá, conta lá mais coisas.
Não tenho mais perguntas. Nem eu.
Mas diz-me lá, na escola já fizeste o exercício dos sismos?
Sim.
Boa, sim senhor, muito bem. No meu tempo ninguém fazia exercício, isso já é uma grande evolução, está bem? Muito bom.
Eu até já fiz. Na minha escola também há um sítio, acho que não é para sismos, acho que é para incêndios, mas nós temos de ir e temos de ficar por turmas.
Exatamente.
E quando há um incêndio, nós subimos um sítio que é relva e depois saímos da escola.
Exatamente, também é o perigo do incêndio que a gente também tem que aprender a responder, sim senhor. Vocês onde é que moram?
Rua
Onde é que moram, assim, em termos gerais? Eu não quero saber nem o nome da rua nem nada, atenção.
Em Lisboa.
Em Lisboa. Então já sabes que Lisboa é uma zona, é uma cidade que já foi destruída por um grande sismo.
Pelo terremoto e pelo 1980.
Epá, sabes muita coisa, pá. Boa. E, portanto, pode acontecer em qualquer altura. Nós temos que estar preparados, está bem? Agora as construções são melhores, portanto, não nos vão cair em cima da cabeça, espero eu, mas temos que nos proteger na mesma, está bem?
Mas foi em 1780. 1980 foi...
O que é que aconteceu em 1980? Diz lá.
Nasceu a minha escola. Foi construída.
A tua escola foi construída em 1980?
Sim.
Isso foi a data de um outro grande sismo, mas esse foi nos Açores. Foi o sismo de 1 de janeiro de 1980. Destruiu Angra do Heroísmo.
Foi dos Capelinhos.
Os Capelinhos ainda foi antes. Isso foi em 1950 e qualquer coisa. Epá, vocês sabem muita coisa.
Uhum. Boa noite.
Então vá, muito obrigado pela vossa presença, está bem? Divirtam-se, divirtam-se.
Bomb. The area where the rock ruptured or broke is small, and the distance the rocks moved is small. A magnitude 4 typically ruptures about 1 square kilometer. A magnitude 6 ruptures about 1. Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake, Rupture, and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and stone conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The light bulb represents the location within the earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb at any spot in a room. A small light bulb in one area of a room will make that area bright with high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps.
drop falling into a pool. If a faucet has a leak, water slowly accumulates as a drop. Over time, the leak continues and the drop grows in size. As it does, the drop's potential energy also increases.
In this case, the drop's potential energy is primarily dependent on the mass of the water and its height.
Eventually, the drop becomes too large to be suspended, and it falls and strikes the surface of the pool below. Energy is transferred to the water in the pool and travels outward in all directions.
Right. The energy travels as ripples on the surface of the water that we can see. However, there are also compression waves that travel outwards through the water unseen.
Like the building of the drop from the faucet, potential energy slowly accumulates in rocks inside the Earth as Earth's tectonic plates.
In this case, the potential energy is primarily dependent on the compressibility and the rigidity of the rocks. Sort of like a spring, the more deformation of the rock, the more energy it stores.
Eventually, the strain becomes so great that the rocks break and the potential energy is suddenly converted to kinetic energy.
Because the sudden release of energy stored elastically in the rocks, an earthquake.
Then, like ripples on the water, the released seismic energy travels outwards in all directions,
including through the earth as seismic waves.
While an earthquake is like ripples on water in many ways, it is also unlike ripples on water in many other ways. Let's re-explore this analogy and note some ways the two are unlike one another. First, a faucet's slow leak can take a while to build up the drop. However, it takes much longer for the potential energy to build up inside Earth.
That's because Earth's tectonic plates only move at a rate of 3 to 5 centimeters per year, or about as fast as your fingernails.
Next, the drop of water falls through the air and strikes the water's surface, while earthquakes occur below the surface of the Earth.
In fact, the deepest earthquakes occur up to about 700 kilometers below Earth's surface.
Once the drop creates the ripples and unseen compression waves in the water, the energy travels outward nearly concentric spheres. This is because the water is essentially all the same material throughout. In Earth, however, seismic waves expand in only roughly concentric spheres.
This is because the speed of the seismic waves is influenced by changes in the geology the waves are traveling through.
Some Earth materials speed up waves, while others slow them down.
Also, seismic waves travel much faster than water waves, nearly 100 times faster.
These are a few key differences between ripples on water and an earthquake. For a more complete description, be sure to explore the links on this page.
When an earthquake occurs, seismologists create graphics of focal mechanisms, informally referred to as beach balls, to show the faulty motions that produce the earthquake. The focal mechanisms are based on the direction of the first arriving P wave. Thus investigate the patterns of P wave arrivals that result from different faulting mechanisms by first considering a strike-slip earthquake. When an earthquake occurs, seismic waves radiate away from the epicenter in all directions. The parallel green lines in the northwest and southeast quadrants have been compressed during the earthquake.
and the northeast and southwest quadrants were stretched. Let's look at the P waves moving away from the epicenter. We will insert slinkies to demonstrate and exaggerate the compression and dilatation features. Northwest and southeast of the epicenter, the rock is compressed, and the first arriving P waves of those stations are pushes away from the epicenter. Northeast and southwest of the epicenter, the rock is stretched, and the first P waves are pulsed toward the epicenter. The dilatational and compressional arrivals are often shown as plus and minus signs, respectively. With observations from many stations, we see two quadrants of compressional arrivals and two quadrants of dilatational arrivals, separated by perpendicular nodal planes. To simplify the illustration, compressional quadrants can be shaded, and dilatational quadrants are left unshaded, producing a P-wave burst motion pattern that looks like a beach ball. Notice that this pattern of dilatations and compressions can be produced either by a right lateral strike slip faulting on a north-south fault plane, or left lateral strike slip faulting on an east-west fault plane. Therefore, you must use geological knowledge of the region to decide which nodal plane is the fault plane. For example, if an earthquake with an epicenter on the San Andreas fault had a focal mechanism that looked like this, the most likely choice would be that the fault plane is oriented northwest to southeast, parallel to the strike of the fault we observe at the surface. Now let's consider a right lateral strike slip earthquake on the Cape fracture zone in the Atlantic. This earthquake will produce compression in the northeast and southwest quadrants, and dilatation in the northwest and southeast quadrants. Since there are no nearby seismometers, the P-wave burst arrival patterns are observed at distant stations. Seismic energy travels away from the earthquake in all directions, so we need to consider the three-dimensional geometry of the ray paths. To do this, it is convenient to imagine a sphere, called the focal sphere, surrounding the earthquake hypocenter. Rays that travel to distant stations will radiate from the earthquake through the lower hemisphere of the focal sphere. To keep things simple, let's look at two cross-sections at more or less right angles. First, make a vertical cut into the earth through the hypocenter in a northeast-southwest orientation. P waves leaving the earthquake and traveling to Lima, Peru in the southwest quadrant, or to Madrid, Spain in the northeast quadrant, will have compressional first arriving P waves that push up, away from the earthquake, and are observed as an initial upward vertical motion on the seismograms. The second cross-section will show P waves traveling to Detroit and Seattle in the northwest quadrant and to Cape Town, South Africa in the southeast quadrant. These will have dilatational first arriving P waves that are pulled toward the earthquake, observed as a downward vertical motion on their seismograms. By examining first arriving P waves at many stations over a range of azimuths and distances from the earthquake, we can determine the pattern of compressions and dilatations on the lower hemisphere of the focal sphere. As we have seen, these strikes of earthquake produces a crossing pattern of approximately vertical faults, or nodal planes that separate two compressional and two dilatational quadrants. Now let's look at the pattern of compressions and dilatations that result from an earthquake on a normal fault, like on the east side of Steens Mountains in the Basin and Range province. The block on the east side of this fault has dropped down with respect to the block on the west. Viewed in cross-section, we see that compressional first arriving P waves will radiate to the east and west from the hypocenter at shallow and intermediate downward angles. Dilatational first arriving P waves leave the hypocenter at a steep downward angle. The resulting focal mechanism has perpendicular nodal planes that cut the lower hemisphere of the focal sphere in an orange slice appearance, with compressions on the outside and dilatations in the center. This is the focal mechanism signature of an earthquake on a normal fault produced by extensional forces. Because of the way the fault plane intersects the bottom of the focal sphere, the boundary between the regions on the focal mechanism is curved. Finally, let's consider a thrust fault, like that beneath Sierra Pie de Paulo, within Sierras Fondeanas of northwest Argentina. This is a west version thrust fault, wherein the block on the east moves up and over the block on the west. Viewed in cross-section, we will see that dilatational first-arriving P waves radiate to the east and west from the hypocenter at shallow and intermediate downward angles, whereas the compressional first-arriving P waves leave the hypocenter at steep downward angles. The resulting focal mechanism has perpendicular nodal planes with the same orange slice appearance observed for normal. However, for a thrust fault earthquake, dilatations are on the outside and compressions are in the center. This cat's eye focal mechanism is the signature of an earthquake on a thrust fault produced by compressional tectonic forces. In 2004, magnitude 9.1 subduction earthquake triggered a tsunami that killed over 230,000 people. Yet a nearby magnitude 8.7 earthquake in 2012 caused little damage and generated minimal ocean waves. Although the earthquakes appeared similar in magnitude and were close in proximity, they were caused by different tectonic processes related to the greater Indo-Australian plate. Two surprising elements of the latter earthquake include it was both the largest interplane earthquake and the largest straight slip earthquake ever recorded. This north-northeast migrating plate is pushing into Eurasia, where an initial ocean continent subduction zone became a continental collision zone with the Asian continent, slowing the northward movement of the plate. Southeast of the Himalayan collision zone, the plate is diving into the Pacific plate. Let's look at the 2004 earthquake in cross-section. The locked plates are moved eastward, building strain between the plates. The magnitude 9.1 earthquake occurred through contact between the plates and they released. The upward thrust generated a tsunami that swept the region. The 2012 earthquake was not in the subduction zone, but was 430 kilometers west of the trend. So what was that about? On April 11, 2012, data captured by a global network of seismologists quickly revealed that this was a powerful straight slip earthquake, which was odd. Earthquakes of this magnitude only occur in subduction zones. To explain it, we'll simplify the setting. Although the combined motion of the Indo-Australian plate and north-northeast, varying deformation of the plate is due to both the distant response to compression of the north, where it's crushing into the Himalayas, and some stretching in the slab fault, where the oceanic plate is diving into the Pacific plate. Geodetic data and plate modeling revealed differential plate motion across the plate. Australia is moving northward 5.6 centimeters, and in India, pushing against the Himalayas is slowed to 3.7 centimeters. This differential movement is resulting in the compression of the plate near the center, where it is slowly being squeezed. Although we're generalizing these movements, the curvature of the Earth makes simple plate motion complicated.
The strain across the broad zone may eventually lead to dividing this plate into two subplates, the Indian and Australian plates along its boundary. Let's look more closely at the actual earthquake in the interplate zone in Corela. The magnitude 8.7 event was not a simple release on a long point. Let's watch what happened. The initial main shock raced along at more than a kilometer second, standing fire coming on a right lateral strike slip fault. That triggered a perpendicular rupture on the left lateral strike slip fault, first to the south, then a second rupture along the same line to the north. 150 kilometers south of the initial rupture, a similar right lateral fault was unfinished. That triggered yet another west-northwest trending fault eruption. Together, this event unleashed the equivalent of 4 magnitude 8 earthquakes, adding together yielding a total event magnitude 8.7, making it one of the most complex earthquakes ever recorded. What caused this complex configuration of the heart of the Indo-Australian plate? Remember, we suggested that according to recent theory, this area is being depressed, as the northern half is being halted by the Eurasian plate, and the southern half is still pushing northward. This area is the process of turning into a subduction zone where one plate, here selected the Australian oceanic part of the plate, will relent in the pushing process and dive beneath the Indian plate, eventually creating an island arc similar to Sumatra and Japan. This process, which began millions of years ago, will take millions more years to form the new boundary, releasing countless earthquakes in the process. What would you do if you have seconds to prepare for shaking from an earthquake that has already begun? More than 143 million people in the United States are exposed to potentially damaging shaking due to earthquakes. Most of our nation's earthquake risk is concentrated in highly populated areas on the active plate tectonic boundaries of the west coast of the continental United States. The U.S. Geological Survey operates the Shake Alert Earthquake Early Warning System, which is part of the Advanced National Seismic System. Shake Alert is not earthquake prediction, but a Shake Alert message issued by the USGS indicates that an earthquake has begun and shaking is imminent. With even a few seconds of warning, Shake Alert can save lives and reduce injuries by alerting people to take a protective action such as drop, cover, and hold on. Shake Alert further protects people and infrastructure by triggering automatic actions such as slowing down trains to prevent derailments, opening firehouse doors so they don't jam shut, and closing valves to protect water systems, and to stabilize equipment during life-critical situations. How does Shake Alert work? When an earthquake occurs, seismic waves carry energy in all directions away from the epicenter. P waves, similar to sound waves, move quickly through the ground, followed by the slower and generally more damaging S waves and surface waves. Sensors detect the seismic waves and send that information to a Shake Alert processing center, which requires that at least 4 sensors detect the earthquake. If the earthquake fits the right profile, the USGS issues a Shake Alert message. Distribution partners then produce and deliver an alert to people and trigger automated systems. Alert delivery can be before, during, or after shaking from S waves and surface waves. Alerts can be delivered to people through apps designed for cell phones and other wireless devices, over public address systems, TVs and radios, and by FEMA's Wireless Emergency Alert System, WEA, which which is also the source of Amber Alerts. For every earthquake, there is a region near the epicenter where alerts will not arrive before shaking begins. That's because close to the epicenter, the P waves are too close together, and the shake alert system needs time, often just seconds, to estimate the earthquake's magnitude and shaking levels before issuing a shake alert message. That means that people close to the earthquake epicenter might not get an alert until after the shaking has already started. Those farther away from the epicenter could receive more warning time before shaking arrives. If an earthquake continues to grow in size, additional shake alert messages might be issued, updating the estimated magnitude and expected shaking for that event, which will result in alerts being delivered to a broader area. The USGS recommends that when you receive an alert, you should take protective action immediately. Do not wait for shaking to arrive. If you are near the coast and a tsunami region, it's important to get to high ground quickly, but only after shaking stops. Before traveling to a new place, learn about both the local hazards and the recommended precautions to take by reading information found in the city, county, or state's emergency management websites. Knowledge of your surroundings and practicing protective actions are critical components of preparedness for any disaster. Always remember, if you receive an earthquake alert or experience shaking, drop, cover, and hold on until all shaking stops. 5.1 seconds after the magnitude 6 Napa earthquake, shake alert test users in San Francisco received warning that the strongest ground shaking would arrive in 8 seconds, vital time to get to safety.
Earthquake, light, shaking, expected in 2 seconds.
How does shake alert work, and how can it be used? When an earthquake occurs, 2 types of seismic waves carry energy away from the hypocenter. P waves, similar to sound waves, have a velocity of about 6 kilometers per second in rock. S waves are slower at 4 kilometers per second, but they have larger amplitude and are generally much more damaging than P waves. Shake alert works by detecting P waves arriving at seismometers closest to the earthquake, sending those signals at the speed of light to a computer system that determines earthquake location and travel times of both P and S waves to your location. Then alerts you on how much time remains before potentially damaging S waves will arrive. You can drop, cover, and hold on with just a few seconds of warning. Unfortunately, if you are too close to the earthquake, you may be in a blind zone that cannot receive a warning. Shake alert does not predict when or where an earthquake will occur. Instead, when an earthquake does occur, shake alert warns you how much time you have before the strongest ground shaking will arrive at your location. If the initial earthquake triggers an ongoing rupture with continuing release of seismic waves, the system recognizes that the magnitude has increased and warns that shaking will be greater than initially predicted. To more fully appreciate the importance of shake alert during major earthquakes, we'll examine the scenario for a hypothetical magnitude 7.8 earthquake on the southern San Andreas Fault. A similar earthquake will happen sometime in the future. We just can't predict when or where. Abrupt movement of rock across a fault starts at the hypocenter, directly below the epicenter location. This shake alert example is aimed to highlight the maximum warning for Los Angeles. Shake alert subscribers closer to the hypocenter will be alerted at the same time, but will receive a shorter early warning before the nearby shaking arrives. Within seconds of the earthquake, P waves arrive at nearby seismometers. Shake alert estimates the magnitude as 7.0 and issues 70 seconds of warning to Los Angeles residents that S waves from the initial rupture will produce weak ground shaking. 5 seconds later, the rupture, shown as the bold pink line along the San Andreas Fault, has grown dramatically, so the magnitude estimate is increased to 7.8, and the expected intensity in LA climbs to moderate. Whereas the magnitude estimate remains at 7.8, Notice that the expected intensity of the largest S waves in LA continues to climb. This is because seismic energy is continually released at the rupture front that is rapidly approaching LA. 22 seconds before small amplitude S waves from the initial rupture reach LA, the expected intensity of the largest S waves released by the approaching rupture is increased to strong. If we look at an oblique view of the Los Angeles basin, we can watch the waves arrive from the southeast. 4 seconds before it reaches LA, the expected intensity is increased to very strong. Notice that the first S waves arriving from the initial rupture are small, but S waves released from the rupture front closer to LA arrive seconds later and produce much stronger ground shaking. Besides providing alerts to drop, cover, and hold on, Shake Alert gives time to get away from dangerous machines or chemicals, shut down gas and electric supply lines, stop rail and road traffic, halt airport takeoffs and landings, stop surgeries, and get emergency personnel ready to respond. Along with construction of earthquake-resistant buildings and infrastructure, coordinated emergency management, and public education, earthquake early warning can help us achieve an earthquake-resilient society.
Sim, vou jantar agora. Sim, estive agora das 8 às 10 a ver se chegava algum cliente. Sim, eu vou agora porque agora são 10 horas. Não,